Look at your hands. Now look at the world around you. The screen you're watching this on, the chair you're sitting in, the air you're breathing. Here's a wild thought. None of this should exist. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. In the very first fraction of a second after the Big Bang, the universe was a perfectly balanced, seething cauldron of creation and destruction. For every single particle of matter that popped into existence, an identical twin was born, an antiparticle. Matter and its mirror image, antimatter, were created in perfect harmony, set on a collision course by the fundamental laws of physics. Their destiny was to wipe each other out, leaving behind nothing but a vast, empty cosmos filled with a faint whisper of light. By all accounts, the universe should be a featureless void. A failed experiment. But something went wrong, or maybe, something went profoundly, miraculously right. An unbelievably tiny error, a cosmic rounding mistake so slight it's almost comical, tipped the scales. This isn't just a story about abstract particles in the distant past. This is the story of the single most important moment in history. It's the story of the fluke that saved everything from nothingness. This is the moment matter almost failed, but didn't. So today, we're going to journey back to the very first microsecond of time itself. We're going to witness the most violent, high-stakes battle imaginable and understand the beautiful imperfection that allows you to be here, right now, wondering about it all. The perfect balance. To get a grip on this crisis, we have to go back to the beginning. Not the beginning of life, or planets, or even stars, but the beginning of everything. Picture the entire universe, all space, all time, all energy, crushed into a point of infinite density and heat. We call this the singularity. And then, in the Big Bang, it began to expand. In the first, impossibly tiny fraction of a second, the Planck epoch, the universe was a place of unimaginable energy. The four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were all squished together into a single, super force. The very ideas of space and time were just starting to take shape. It was a realm so extreme our current physics can barely peek over the fence. But as the universe expanded, it cooled. And just like steam condenses into water, this primordial energy began to condense into the first fundamental particles. This is where the perfect, deadly symmetry of our story begins. Einstein's famous equation, E equals mc squared, is a two-way street. It doesn't just say matter can become energy, it also says energy can become matter. In the searing heat of the early universe, this process, called pair production, was happening constantly. Pure energy was spontaneously morphing into pairs of particles. For every electron, a positron, its antimatter twin, same mass but opposite charge, was created. For every quark, an antiquark was born. The universe was a frantic, boiling soup where matter and antimatter continuously flashed into and out of existence. This was the quark-gluon plasma, a state so hot and dense that protons and neutrons couldn't even form. Quarks and the gluons that bind them just zipped around freely in a perfect, chaotic dance. Less like a gas and more like a nearly frictionless, perfect liquid. Think of it like this. You have a bank account with a limitless overdraft of pure energy. You can withdraw from it anytime, but there's one rule. For every dollar of matter you take out, you must also take out $1 of antimatter. The books must always be balanced. The net stuff in the universe stayed at zero. You had a cosmos filled to the brim with particles, but it was all an illusion, a temporary loan from the bank of energy. The laws of physics had created a perfect, beautiful, and utterly doomed symmetry. Because just as easily as energy could create these pairs, the pairs could find each other. And when they did, they'd pay the debt back in a flash of pure energy. This is annihilation, and it was a ticking time bomb at the heart of the newborn cosmos. The annihilation problem. The law is simple and brutal. When a particle of matter meets its antiparticle, they annihilate. They vanish, their mass converted back into pure energy, usually in the form of high-energy photons, particles of light. In that primordial soup, this was happening on a scale that's hard to wrap your head around. A quark and an anti-quark would be born from energy, fly apart for an instant, and then smash into other partners, annihilating back into the energy they came from. Creation and destruction, locked in a perfect, furious stalemate. But the universe kept expanding, and as it expanded, it cooled. This cooling is the engine of our entire cosmic story. As the temperature dropped, the universe's energy levels fell below the threshold needed to create the heaviest particles. The cosmic bank was starting to lower its credit limit. About 1 microsecond after the Big Bang, the universe had cooled enough for quarks and anti-quarks to start clumping together. This marks the start of the Hadron Epoch. Quarks formed into groups of 3 to make baryons, like protons and neutrons. Anti-quarks formed antiprotons and antineutrons. For a brief moment, the universe was filled with these new, more complex particles and their antimatter twins. But the fundamental rule still applied. A proton would find an antiproton. A neutron would meet an antineutron. And in a flash of gamma rays, poof! Gone. The same fate awaited the lighter particles in the lepton epoch that followed. Electrons found positrons, and they too disappeared in puffs of energy. And here's the paradox, the moment of cosmic failure. If the Big Bang produced matter and antimatter in perfectly equal amounts, as all the physics we knew suggested, then this process of annihilation should have been total. For every single particle, there was an anti-particle dance partner waiting to embrace it into oblivion. As the universe cooled, creating new pairs would slow down and stop, but the annihilation would go on until there was nothing left. The universe should be empty. Not empty like the space between galaxies, which is actually buzzing with stray atoms, radiation, and dark matter. It should be truly, fundamentally empty. No matter. No galaxies, no stars, no planets, no people. The entire cosmos would just be a vast, dark, silent sea of photons. The leftover energy from that final, universe-ending demolition. It's the logical, inevitable conclusion of a perfectly symmetric beginning. But just look around. We are here. The stars are burning. This means the logical conclusion was wrong. The perfect symmetry must have been broken. The annihilation wasn't total. Physics had predicted a perfect, beautiful, sterile universe. But the reality we live in is the result of an imperfection, a flaw in the grand design. The critical question, the one our very existence hinges on, is: what was that flaw? What was the cheat code that allowed matter to win? The 1 in a billion fluke. The answer, when physicists crunched the numbers, was almost laughably small. Matter didn't win by a landslide. It was a statistical squeak. The evidence points to a stunning conclusion. For every 1 billion antimatter particles in the early universe, there were something like 1 billion and 1 asterisk matter particles. 1 in a billion. Let that sink in. Picture a billion furious annihilations, a billion pairs of particles turning to light. After all that carnage, all that cosmic demolition, just 1 lonely matter particle is left behind. That's it. That's the surplus. That tiny remnant is the source of every single proton, neutron, and electron in the universe today. Everything you've ever seen or touched is part of that 1 in a billion leftover crew. The rest is just radiation, the echoes of that great annihilation, which we can still detect today as the cosmic microwave background. The universe is, in a very real sense, 99.9999999% of the way to being empty. We are living in the rounding error. So, this wasn't a fair fight. It was rigged from the start, even if by the slimmest of margins. But how? How could the laws of physics contain such a subtle, yet world-defining, bias? In 1967, the brilliant Soviet physicist Andrei Sakharov came up with a recipe for existence. He outlined 3 conditions that must be met for a universe to start symmetric but end up with a matter surplus. They're now known as the Sakharov conditions. First, baryon number violation. This is the big one. Baryon number is basically a quantum accounting trick. Baryons, like protons, have a baryon number of +1. Antibaryons have -1. In just about every interaction we've ever seen, this number is conserved. If you start with 2 baryons, you have to end with 2. But Sakharov said this rule had to be breakable in the early universe. There had to be a process that could change the total baryon number. A way to create matter without an equal and opposite antimatter reaction. The books had to be cookable. Second, C and carbon monophosphide symmetry violation. This is where the bias, the thumb on the scale, comes from. CP symmetry basically says that the laws of physics should be the same for a particle and its mirror reflected antiparticle. For decades, this was assumed to be a perfect symmetry. But in 1964, an experiment showed that for some weird particles, this symmetry is slightly violated. The universe, at a very subtle level, does treat matter and antimatter differently. It has a slight preference. Sakharov knew this was the key. You need a reason for the rule-breaking process to favor matter. CP violation is that reason. And just recently, a groundbreaking discovery from the LHCb experiment at CERN confirmed this exact type of CP violation in baryons, the very building blocks of matter, proving they and their antimatter counterparts don't decay in exactly the same way. It's a huge piece of the puzzle, a clear crack in nature's mirror. Third, a break from thermal equilibrium. This last one is what seals the deal. Thermal equilibrium is a state of perfect balance, where all processes are happening at the same rate, forwards and backwards. Creation matches annihilation. If the universe had stayed in this placid state, any tiny imbalance would have been immediately smoothed over and erased. You need to shake things up. In the early universe, that disruptive event was its own ridiculously fast expansion and cooling. The universe was changing so quickly it was thrown out of equilibrium. Processes fell out of sync. Before the universe could erase the tiny matter surplus, the temperature dropped so fast that the reactions that could reverse the process simply froze out. They stopped happening. The rapid expansion locked in the imbalance. It preserved the fluke. These 3 conditions, working together, provided the loophole that matter needed to survive. The victory of matter. With the conditions met and the scales tipped, the stage was set for the final act. The universe was still a battlefield, but the outcome was now fixed. As the great annihilation raged on, for every billion antimatter particles that met their end, one matter particle was left without a partner. A sea of photons, the ghosts of the annihilated pairs, now vastly outnumbered the remaining particles, but these photons were just energy. The universe was too cool for them to create new pairs. All that was left to build a future with was the particulate ash of the Great Fire, the matter surplus. As the universe crossed the 1-second mark, things began to calm down. The surviving protons and neutrons, no longer under constant threat, started to find each other. The universe was now cool enough for the strong nuclear force to start building things. This was the beginning of nucleosynthesis. For the next 3 to 20 minutes, the entire universe was one giant nuclear reactor. Protons, which are just hydrogen nuclei, began fusing with neutrons to form the first complex atomic nuclei. Deuterium, then helium, with tiny traces of lithium. By the end of this era, the raw material of the cosmos was locked in, about 75% hydrogen and 25% helium by mass. This prediction is one of the most stunning successes of the Big Bang model, Because it perfectly matches the composition of the oldest stars and gas clouds we see today. It's a chemical fingerprint left at the scene of the crime. But even with nuclei, the universe was still an opaque fog. The sea of leftover photons was still energetic enough to knock any electrons away from the nuclei, keeping everything in a glowing, impenetrable plasma. Light was trapped in an endless game of cosmic pinball. This went on for 380,000 years. Then, the universe cooled to a critical milestone, about 3000 Kelvin. The photons finally lost enough energy that they couldn't bother the electrons anymore. This moment is called recombination. For the first time, stable, neutral atoms could form. Electrons were captured by nuclei, and the universe's long-standing fog cleared. The photons, finally free, streamed across the cosmos. That liberated light is what we now detect as the cosmic microwave background, CMB. When we point our telescopes at the sky, we are seeing the baby picture of the universe, the afterglow of the Big Bang. The CMB isn't perfectly uniform, it has tiny temperature fluctuations. Those fluctuations are the seeds from which all future structure would grow, the first signs of gravity pulling the victorious matter into the clusters that would one day become galaxies, stars, and us. The unsolved mystery. So, the story seems complete. Problem: the annihilation paradox. Solution: a 1 in a billion imbalance. Evidence: a universe full of stuff and the cosmic microwave background. But in science, a how is always followed by a why. It's one thing to say the Sakharov conditions were met, but it's another thing entirely to pinpoint the specific particle or force that did the dirty work. This is one of the biggest unsolved mysteries in physics. The prime suspect, the standard model of particle physics, just isn't up to the job. It does have a mechanism for CP violation, but it's many, many orders of magnitude too weak to explain the asymmetry we see. This is a huge clue. It tells us there must be new physics out there, something beyond what we currently know. The hunt for this new physics is happening right now, at colossal machines like the Large Hadron Collider. And it's yielding results. The recent discovery of CP violation in baryons was a monumental confirmation of Sakharov's theory, proving the universe's bias is real. But that still doesn't explain the asterisk scale of the imbalance. So what could? Two leading theories are vying for the top spot: electroweak baryogenesis and leptogenesis. Electroweak baryogenesis suggests the matter was created during the electroweak phase transition, about 10 picoseconds after the Big Bang, when the electromagnetic and weak forces split apart. The idea is that this transition was violent, like boiling water. Bubbles of the new state of the universe formed and expanded. The walls of these bubbles were zones of extreme chaos, perfect for satisfying Sakharov's conditions and sorting matter from antimatter, pushing slightly more matter into the bubbles. The catch? This model needs new, undiscovered particles to make the transition violent enough. The other top contender is a beautifully subtle theory called leptogenesis. It suggests the imbalance didn't start with matter particles like protons at all. It started with leptons, like electrons and their mysterious cousins, neutrinos. The theory proposes the existence of a very heavy, undiscovered type of neutrino. As these heavy neutrinos decayed in the early universe, they could have done so asymmetrically, producing slightly more leptons than antileptons. So how does that create the matter we see? Through a strange quantum loophole called the Sphaleron process, which was only active at extreme temperatures and can convert leptons into baryons. If you feed this quantum alchemy machine in excess of leptons, it spits out an excess of baryons to try and restore balance. What makes this theory so compelling is that these heavy neutrinos could also solve another huge mystery: why the neutrinos we see today have any mass at all. The two biggest puzzles beyond the standard model might be two sides of the same coin. Experiments like the Deep Underground Neutrino Experiment, DUNE, are being built right now to study neutrinos with incredible precision, which could tell us if this elegant theory is correct. The search continues. Each new piece of data brings us closer to understanding the precise mechanism that tilted the cosmic scales, and closer to a new layer of reality hidden from us since the first picosecond of time. Conclusion. From a point of infinite energy to a war of annihilation that should have left nothing but light, the story of our universe is the story of an imperfection. A grand cosmic drama where the laws of physics themselves contained a hidden flaw, a subtle bias that allowed an escape from the void. Every atom in your body, every star in the night sky, is a direct descendant of that tiny, 1 in a billion leftover fraction. We are the survivors of the moment matter almost failed. The universe we inhabit wasn't the result of a perfect plan, it was the result of a beautiful, existence-granting mistake. It's a humbling thought. When you look up at the vastness of the cosmos, remember that it is all built from the ashes of a near-perfect demolition. It's a testament to the power of a tiny imbalance. And in a way, it's a hopeful one. It suggests that it's the imperfections, the slight deviations from the plan, that create the most interesting and beautiful outcomes. Without that fluke, none of us would be here to wonder about it at all. What part of this story blows your mind the most? Let me know your thoughts in the comments. And if you enjoy exploring these deep questions about where we came from, make sure to subscribe so you don't miss our next journey into the unknown. Thanks for watching. The first second that almost erased the universe. Before there were stars, before there was light, before time and space meant anything, the entire future of the universe was balanced on a knife's edge. In the very first flicker of existence, a cosmic coin was tossed. On one side, a universe teeming with trillions of galaxies, with planets, life, and consciousness. On the other, an eternal, silent, featureless void. For a fraction of a moment, the fundamental fields of reality, the very essence of you and me, threatened to collapse into chaos. A quantum tremor that would have stopped a single stable atom from ever forming. This is the story of that moment. This is the story of the first second that almost erased our universe before it ever truly began. Setting the stage. To understand this cosmic gamble, this moment of creation or total annihilation, we have to do something that feels impossible. We have to forget everything we think we know about reality. Go on, press your hand against a table. It feels solid, right? Real. Your hand, an object with mass, is being stopped by another object with mass. But that feeling, as real as it is a profound illusion. Your hand isn't actually touching the table. The atoms in your fingers aren't physically bumping against the atoms in the wood. What you're feeling is far stranger. The near-instant repulsion of invisible force fields. The electrons in your atoms are aggressively pushing away the electrons in the table's atoms, all governed by a set of invisible rules. The world isn't made of stuff. It's made of rules, and those rules were never guaranteed. They had to be chosen. They had to win a cosmic lottery against an infinity of other possibilities, most leading straight to oblivion. Our journey today rewinds the clock 13.8 billion years. To an era so early and violent it's hard to even describe with our language. We'll explore what matter really is, not solid particles, but fragile, shimmering ripples in invisible, universe-spanning oceans called quantum fields. And then, we'll travel to the very first moment, the Planck epoch, a time when these fields were a raging, chaotic mess, on the verge of failing to ever produce a single stable thing. By the end of this, the solid world around you will look less like a collection of objects and more like a frozen symphony. A fragile harmony of vibrating fields. A structure built from rules that almost never came to be. You'll see that your own existence is the result of the universe pulling back from the brink at the last possible nanosecond. Deconstructing reality, the myth of solid stuff. Our first step is to dismantle the reality we perceive every day. That feeling of solidity you get from the chair you're on, the ground beneath your feet, it's a lie. A very convincing one, but a lie nonetheless. The story of our universe is the story of emptiness, governed by powerful principles that create the asterisk illusion of substance. Let's start with the atom. We picture it as a tiny solar system, a dense nucleus with electrons orbiting like planets. But that picture is misleading. An atom is almost entirely empty space. If you scaled up an atom so its nucleus was the size of a marble in the center of a football stadium, the electrons would be like grains of dust whirling around the furthest seats. Everything in between? Nothing. Your body, the earth, the sun, all of it is 99.999999% empty space. So, if you and the chair you're on are both almost entirely nothing, why don't you fall right through it? The answer is our first cosmic rule, the Pauli exclusion principle. Formulated by physicist Wolfgang Pauli, its decree is surprisingly simple. No two identical matter particles can occupy the exact same quantum state at the same time. Matter particles, like electrons, are part of a family called fermions. You can think of them as the universe's ultimate individualists. They refuse to be in the same place with the same properties. When the electrons in your hand approach a wall, they can't just pass through. All the available quantum rooms in the wall's atoms are already occupied. To pass through, your electrons would have to take states already taken by the wall's electrons, and the exclusion principle forbids this with the force of law. What you perceive as touch is the immense resistance from trillions of electrons fiercely defending their personal space. They aren't touching, they're repelling. Solidity isn't a property of matter. It's the consequence of a rule that keeps empty space from passing through other empty space. But this only deepens the mystery. If matter is just empty space held apart by a rule, what about its mass? What gives you weight? Here again, our intuition gets turned on its head. In the 1960s, physicists' theories had a fatal flaw. They predicted all fundamental particles should be massless, zipping around at the speed of light. This was obviously wrong. Something had to be giving particles their heft. The solution was a radical idea from Peter Higgs and others. They suggested the entire universe is filled with an invisible energy field, the Higgs field. Think of it like a kind of cosmic molasses permeating all of space. Some particles, like photons, feel no interaction with this field, so they glide through it effortlessly at light speed. Others, like electrons and quarks, have to wade through it. This drag, this interaction, is what we perceive as their mass. A particle isn't inherently heavy, it becomes heavy because of its struggle to move through the Higgs field. But here's where it gets truly mind-bending. The mass you get from the Higgs field is only a tiny fraction of your total mass. A proton is made of 3 smaller particles called quarks. If you add up the masses the Higgs field gives these 3 quarks, you get only about 1% of the proton's total mass. So where does the other 99% come from? The answer is pure energy. Inside a single proton, those 3 quarks are bound together by the strong nuclear force. This force is carried by particles called gluons, and they create a field of such immense tension it's almost impossible to comprehend. The quarks move at nearly the speed of light as the gluons furiously work to keep them contained. According to Einstein's famous equation, E equals mc squared, energy and mass are 2 sides of the same coin. The colossal amount of binding energy within the proton, the sheer energetic chaos of quarks and gluons rattling around in their tiny prison, accounts for the other 99% of its mass. Let that sink in. The you that gives you weight and presence isn't from fundamental stuff. It is almost entirely the raw, seething energy of fields binding other fields together. You're not a collection of tiny marbles. You're a stable, intricate pattern of pure energy, solidified by a handful of cosmic rules that had to be written just right. The real foundation, A universe of fields. So we've torn down the familiar world of solid objects to reveal a stranger reality. A universe of mostly empty space, where the illusion of substance is generated by invisible forces and fields. Now, let's build that reality back up from its true foundation, quantum field theory. The central idea of quantum field theory is simple and world-shattering. The most fundamental component of the universe isn't particles. It's fields. You've encountered fields before. Hold two magnets apart, and that push or pull you feel is a magnetic field. The reason you're stuck to your chair right now is Earth's gravitational field. Now, imagine that everything is a field. Imagine a universe completely filled with overlapping, invisible, vibrating sheets of potential. There's an electron field that permeates every cubic centimeter of space. There's a quark field, a photon field, and so on. In the current standard model, reality is described by 17 of these fundamental fields. So if the universe is just invisible fields, where are the particles? According to quantum field theory, a particle is nothing more than a vibration, a localized, excited ripple, in its corresponding field. Imagine a perfectly calm ocean stretching to the horizon. That's a field in its lowest energy state. Now, tap the surface of the water. A ripple spreads outwards. That ripple, that localized packet of energy, is the particle. An electron is a ripple in the electron field. A photon of light is a ripple in the electromagnetic field. When we see a particle, we're really seeing one of these fields vibrating at a specific spot. This completely changes our picture of reality. Particles aren't tiny, solid balls. They are temporary excitations. They can be created and destroyed. Put enough energy into the electromagnetic field, and a photon can be born from the vacuum. When a particle and its antiparticle meet, they are two ripples that cancel each other out, and their field settles back down, releasing its energy as a flash of light. This leads to an even more bizarre consequence. What we call empty space isn't empty at all. The vacuum is just the state where all these quantum fields are at their lowest possible energy. But lowest possible doesn't mean zero. Thanks to the Heisenberg uncertainty principle, these fields can never be perfectly still. They constantly hum with a minimum energy, a nervous tremor known as zero-point energy. Out of this simmering energy, virtual particles constantly pop into existence and annihilate each other, a chaotic fizz sometimes called quantum foam. The vacuum isn't a silent void, it's a boiling cauldron of potentiality. This is the true nature of our reality. Not a collection of durable objects, but a delicate dance of 17 fundamental fields, whose vibrations we interpret as particles. The universe is a symphony, and particles are just the notes being played. But this symphony is incredibly fragile. For these fields to settle down and produce the stable particles needed for atoms and galaxies, the conditions had to be just right. Now, with this new understanding, let's rewind the clock. We're going to the very first tick, a moment of unimaginable violence and instability. We're going to the Planck epoch. The moment of creation, the Planck epoch. Now we arrive at the heart of our story. We're rewinding 13.8 billion years to the most extreme and mysterious moment in cosmic history, the Planck epoch. This era lasted from time 0 to roughly 10 to the power of 4 cubed seconds. That's a decimal point followed by 42 zeros and a 1. A duration so short that if you scaled the age of the universe to 1 second, the Planck epoch would be over 1 billion trillion times faster than you can blink. The conditions were beyond all comparison. The entire observable universe was compressed into a space smaller than a proton. The temperature was a staggering 10 to the power of 32 Kelvin. At this temperature and density, our familiar laws of physics break down. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, are thought to have been merged into a single, unified, superforce. It was a state of perfect, yet terrifyingly unstable, symmetry. In this primordial furnace, our universe faced a series of existential threats, each with the potential to erase reality before it could begin. This was the moment of the great cosmic coin toss, and the universe almost lost. Cosmic problem number 1. The chaos of quantum foam. In our universe, spacetime is smooth. It's a stable stage for quantum fields to vibrate on. But in the Planck epoch, the very fabric of spacetime is thought to have been a chaotic, violent, roiling mess. Physicists call it quantum foam. Spacetime itself was twisting, bubbling, and tearing apart. Remember our particle as a ripple on a calm ocean? How can you have a stable ripple on an ocean being thrashed by a hurricane? You can't. In the Planck epoch, the quantum fields had no stable ground to stand on. Any vibration that might have become a particle would have been instantly torn apart by the churning chaos of spacetime. Cosmic problem number 2. The furnace of annihilation. Even if spacetime were stable, the sheer energy was a lethal barrier. The temperature of 10 to the power of 32 K was a furnace of creation and instant annihilation. Particles and their antimatter counterparts were spontaneously created from raw energy, only to collide and annihilate each other a moment later. This state was even more primordial than a quark-gluon plasma. There was no chance for quarks to cool and bind together. Any structure was immediately dissolved back into pure energy. The universe was trapped in a frantic loop of creation and destruction, an equilibrium of nothingness. Cosmic problem number 3. The indecision of the Higgs field. This is perhaps the most subtle and most terrifying problem. As we discussed, particles get their mass from the Higgs field. But in the ultra-hot Planck epoch, the Higgs field was switched off. Its value everywhere was zero, meaning all particles were massless. This state is profoundly unstable, like a pencil balanced perfectly on its tip. It's symmetrical, but the slightest tremor will cause it to fall. The crucial question is, which way will it fall? The Higgs field was this balanced pencil. As the universe expanded and cooled, the Higgs field had to fall from zero and settle into a new, non-zero value. But it wasn't guaranteed to fall to the asterisk right value. The value it settled on, about 246 giga-electron volts, was a critical piece of the puzzle that allowed particles to gain the properties needed to form the structures we see today. What if it had fallen to a different value? Or remained at zero? If electrons had stayed massless, they would forever zip around at the speed of light, never forming atoms. If quark masses were slightly different, protons might have been unstable. A universe with slightly different particle masses could be a universe with no chemistry, no stars, and no life. For a moment, all of existence depended on this quantum roll of the dice. Cosmic problem number 4. The threat of total collapse. The final threat was the breakdown of physics itself. The Planck epoch is where general relativity and quantum mechanics must merge. Yet, when we try to combine them mathematically, they produce nonsense. We don't have a working theory of quantum gravity. In this lawless regime, gravity could have been the ultimate destroyer. The immense density of the infant universe could have caused it to immediately collapse back in on itself into a black hole. There was no guarantee that the universe should expand. The Big Bang could have ended as a big crunch, less than 10 to the power of 4 cubed seconds after it began. So there it was, a universe balanced on a knife's edge. A chaotic spacetime, a furnace of annihilation, an indecisive fundamental field, and the looming threat of total collapse. For the universe to become what it is, it had to win an impossible lottery, not once, but 4 times in a row. The Great Escape. How the universe survived. Our infant universe was trapped, teetering on the verge of non-existence. What happened next was a jailbreak of cosmic proportions, driven by a mechanism so bizarre it still stretches our imagination. This was the moment the universe played its trump card. The hero of our story is a theory known as asterisk cosmic inflation. Proposed in the late 1970s and early 1980s by scientists like Alan Guth, this idea radically transformed our understanding of the Big Bang. It suggests that for a fleeting moment, from around 10 cubed to the power of 6 to 10 cubed squared seconds, the universe underwent a period of mind-boggling, exponential expansion. It wasn't just expanding, it was inflating. In this tiny fraction of a second, the universe is thought to have doubled in size at least 80 times, growing from a scale smaller than a proton to something roughly the size of a grapefruit. It expanded faster than the speed of light. That sounds impossible, but it isn't. Nothing can travel through space faster than light, but there's no limit on how fast space itself can expand. And it expanded with ferocious speed. This single event was the key to our salvation. How inflation solved the problems. The cosmic refrigerator. First, inflation acted as a cosmic steamroller. That chaotic, bubbling quantum foam of spacetime? As the universe expanded at this incredible rate, all those violent wrinkles were stretched out and smoothed away. Imagine the crinkled surface of a balloon. As you rapidly inflate it, the surface becomes incredibly smooth. Inflation did the same to the fabric of spacetime, creating the vast, smooth stage our quantum fields needed. Crucially, this rapid expansion also acted as a cosmic refrigerator. Just like compressed gas cools as it expands, the explosive growth of inflation caused the universe's temperature and energy density to plummet. The primordial furnace was suddenly chilled, signaling a profound change of state, much like water freezing into ice. The pencil falls. The Higgs field chooses our reality. As the universe cooled, the perfect, unstable symmetry was broken. The balanced pencil fell. The unified, superforce fractured into the forces we know today. And most importantly, the Higgs field, no longer sustained by extreme heat, relaxed from its zero state and settled into its new, permanent, non-zero value across all of space. This was the moment of electroweak symmetry breaking. As the Higgs field settled, it permeated the universe with the cosmic molasses that gives certain particles mass. Suddenly, particles like electrons and quarks acquired their mass. They slowed down. They became capable of being captured and forming structures. The coin toss had landed in our favor. The Higgs field had chosen a value that would allow for a universe of complex chemistry and, eventually, life. The strong force awakens, forging the first matter. With the universe now cooler and filled with massive quarks and electrons, another hero entered the stage. At about 1 microsecond after the Big Bang, the universe had cooled enough for the strong nuclear force to begin its work. During the hotter era, the universe was a quark-gluon plasma, a soup of free quarks and gluons. But now, the strong force became overwhelmingly powerful at short distances. It acted like cosmic glue, grabbing free-roaming quarks and confining them into groups of 3. This confinement created the very first stable particles, protons and neutrons. For the first time, the universe had the building blocks of atomic nuclei. The first durable, matter, had finally emerged from the chaos. The final gamble, matter versus antimatter. The universe had survived, but one final hurdle remained. The laws of physics tell us that when energy becomes matter, it must create an equal amount of antimatter. But if the balance had been perfect, disaster would have struck. As the universe cooled, every particle would have found its antimatter twin and annihilated, converting all the matter in the universe back into a sea of pure light. The cosmos would be beautiful, but sterile and empty. Somehow, that's not what happened. For reasons that are still one of the greatest mysteries in physics, the laws of nature seem to have a slight preference for matter. The leading theory, outlined by physicist Andrei Sakharov, proposes the conditions for this, but it's not yet proven. The result was a tiny, almost imperceptible imbalance. For every 1 billion antimatter particles, the universe created 1 billion and 1 matter particles. It was a cosmic rounding error. But it was everything. After the great annihilation was over, that tiny 1 in a billion surplus of matter was left. Everything you see, every star, every planet, every atom in your body, is the result of that final, lucky imbalance. We are the leftovers from the greatest vanishing act in history. This incredible journey, from the brink of chaos to a cosmos fit for life, was made possible by a precise set of fundamental rules. If you could ask the universe a question about one of these cosmic rules that saved us, what would it be? What mystery fascinates you the most? Let us know in the comments below. And if you enjoy exploring these profound questions about our reality, please consider subscribing and hitting the like button. It helps us continue to journey to the very edge of what we know. Conclusion. From the violent, lawless chaos of the Planck epoch, our universe emerged. It survived a trial by fire, navigating a minefield of existential threats, each of which could have led to nothingness. The story of that first second is the ultimate cosmic drama, a story of near disaster and incredible luck. The vast, silent galaxies we see today are the direct descendants of those infinitesimal quantum fluctuations from the inflationary era, stretched to astronomical proportions. The cosmic microwave background, the faint afterglow of the Big Bang, carries the fossilized evidence of the universe's great escape. So the next time you look up at the night sky, or feel the solid ground beneath your feet, remember what you really are. You're not a static object made of stuff. You are a 13.8 billion-year-old process. You are a stable pattern of vibrating quantum fields, a delicate harmony of forces held in an intricate dance. A dance that was almost cancelled before the music even began. The solid world is the greatest illusion of all. It's a testament to the fact that reality is not built from things, but from rules. And we are profoundly lucky that in the very first second, in the greatest cosmic coin toss of all time, the universe chose the rules that allowed for stars, for planets, and for us to be here, wondering about it all. The 1 in a billion glitch that created the universe. According to the most fundamental laws of physics, you shouldn't exist. In fact, nothing should exist. Not the screen you're looking at, not the planet you're on, nothing. In the very first, searingly hot moment of creation, the universe followed its own rules perfectly. For every single particle of matter that exploded into existence, an equal and opposite particle of antimatter was born. Their fate was sealed the instant they appeared. Find each other, collide, and annihilate, leaving behind nothing but a sea of pure light. A perfect cancellation. If that's what happened, the universe should be a complete and utter void. An endless, empty expanse, home to nothing but fading radiation. So, why is there something, instead of nothing? Because in that first fraction of a second, the universe did something it was never supposed to do. It broke its own rules. It made a mistake. This is the story of the 1 in a billion glitch that tore up the blueprint for an empty cosmos and allowed for everything you have ever known to exist. The perfect universe that never was. To get why this glitch is such a big deal, you first have to appreciate the perfect universe it wrecked. In physics, symmetry isn't just about a pretty pattern. It's one of the deepest ideas we have, that the laws of nature are consistent and unchanging, no matter how you look at them. Run an experiment today or tomorrow, here or on Alpha Centauri, and the rules stay the same. This idea is captured beautifully in Noether's theorem, dreamt up by the brilliant mathematician Emmy Noether. Basically, her theorem says that for every symmetry in nature, there's a corresponding thing that must be conserved. Because the laws of physics don't change over time, energy is conserved. Because the laws are the same everywhere in space, momentum is conserved. Symmetry is order. It's predictability. And for a long time, physicists were convinced there was a crucial symmetry between matter and its bizarre twin, antimatter. Antimatter isn't just sci-fi nonsense, it's breathtakingly real. Its existence was first predicted back in 1928 by physicist Paul Dirac. He was trying to merge Einstein's relativity with the strange new world of quantum mechanics, and his elegant equations kept spitting out a weird quirk. Two solutions. One described the familiar electron, but the other described a particle with the exact same mass, but the asterisk opposite charge. An anti-electron. Dirac and his colleagues were stumped. What could it possibly mean? Then, just 4 years later, a physicist named Carl Anderson was studying cosmic rays and found the unmistakable track of Dirac's phantom particle. He called it the positron. Antimatter was real. Since then, we've found and even created antiprotons, antineutrons, and whole antiatoms in labs like CERN. The most important thing about these twins is their toxic relationship. When a particle of matter meets its antiparticle, they don't just bump into each other. They annihilate. Their entire mass is converted into a flash of pure energy, exactly like Einstein's famous E=mc² predicts. We can watch this happen on demand. We even use it in medical PET scans, where annihilating positrons help doctors see what's happening inside the human body. Now, let's rewind the clock 13.8 billion years. The Big Bang. The universe was an incandescent point of nearly infinite energy. As it expanded and cooled, that energy turned into mass. But because of physics's obsession with symmetry, this process, called pair production, should have been perfectly balanced. For every electron, a positron. For every quark, an antiquark. 1 for 1. A perfect match. This balance, however, was a death sentence. In the dense, chaotic soup of the early universe, no particle could go far without bumping into its anti-twin. And when they met, poof, annihilation, a flash of light, every single time. If this had gone on flawlessly, as the laws of symmetry demanded, the outcome was inevitable. Every last particle of matter would have found an antiparticle. The grand cosmic dance would have ended in a final, universe-spanning flash of mutual destruction. What would be left? A vast, silent, featureless expanse. A universe filled with nothing but a dilute, cooling gas of photons, the leftover light from all that annihilation. No stars, no galaxies, no planets, no chemistry, no biology, no life. Just a thin, fading glow, the ghost of a universe that could have been. This is the perfect universe predicted by the laws of physics. And it is the most terrifyingly wrong prediction in the history of science. Because you are here, I am here. Hundreds of billions of galaxies are here. Our existence is the ultimate proof that something went profoundly wrong. The cosmic crime scene. So just how wrong was this perfect prediction? The evidence, written in the faint afterglow of the Big Bang, tells us the ratio. For every 1 billion pairs of matter and antimatter particles that destroyed each other, a single, solitary particle of matter was somehow left behind. Not 1 in a million. Just 1 in a billion. That tiny residue, this fractional rounding error in the cosmic books, is everything. Look around you. Everything you can see and touch is made of those leftovers. Every atom in your body is a descendant of one of those lone survivors that dodged the great annihilation. You are made from a 1 in a billion glitch. So how did it happen? To solve this mystery, we have to become cosmic detectives. In 1967, the brilliant Soviet physicist Andrei Sakharov laid out the 3 conditions that were absolutely necessary for this to happen. Think of them as the motive, the weapon, and the opportunity for this cosmic crime. First, the motive. Baryon number violation. Baryons are particles like the protons and neutrons that make up atoms. Baryon number is just a way of keeping count. Protons get a +1, antiprotons get a -1. In every experiment we've ever run, this number is conserved. If you make a proton, you also have to make an antiproton. The total count never changes. But Sakharov argued that in the insane energies of the Big Bang, this rule could be broken. This opens the door to creating more matter than antimatter. Second, the weapon. Violation of CP symmetry. This sounds complex, but it's really about two ideas. C symmetry says physics should be the same if you swap a particle with its antiparticle. P symmetry, or parity, says the mirror image of a process should also be possible. For a long time, we thought the universe obeyed both. Then, in the 1950s, a shocking discovery showed that one of the fundamental forces, the weak force, violates P symmetry. The universe can tell left from right. Physicists were stunned but figured a combined carbon monophosphide symmetry, swapping a particle for its mirror-imaged antiparticle, must still hold. Then came 1964. An experiment studying weird particles called kaons found that even carbon monophosphide symmetry was broken. The universe, it turns out, does not treat matter and antimatter as perfect mirror images. The laws of nature themselves have a tiny, built-in bias. This was the smoking gun. This was the weapon that proved the universe is capable of picking a favorite. But a motive and a weapon aren't enough. You need the opportunity. This is Sakharov's third condition, a * departure from thermal equilibrium. If the early universe had stayed in perfect balance, any process that created an extra matter particle would have been perfectly cancelled out by a reverse process. The books would always balance. The opportunity came from the explosive expansion of the universe itself. The Big Bang wasn't a gentle unfolding. It was a violent expansion that caused the temperature to plummet almost instantly. This rapid cooling threw the universe out of balance. It was changing too fast for all the reactions to keep up. It's like flash freezing a pot of boiling water. The matter creating reactions, slightly favored by that carbon monophosphide violation, ran for a split second. But before the universe could correct its error with the reverse reactions, the temperature dropped, the energy levels fell, and those reverse reactions effectively shut off. The glitch was locked in. The tiny surplus of matter was now frozen into reality. The universe had successfully cooked its books. The glitch in the matrix. The 1964 discovery was our first hint of the glitch, but was it just a fluke? And more importantly, was this tiny effect big enough to explain the 1 in a billion imbalance? To find out, physicists built dedicated B factories in the US and Japan. Their mission? To mass produce and study particles called B mesons. They succeeded, confirming that B mesons also violate carbon monophosphide symmetry, proving the glitch was a real, recurring feature of the universe. The hunt then moved to the Large Hadron Collider at CERN. Deep underground, the LHCb experiment was designed to be the ultimate CP violation hunter. By smashing protons together, it creates a storm of exotic particles. Just recently, they announced the first observation of CP violation in baryons, the family of particles that includes our own protons and neutrons. They found a small but undeniable difference in how certain beauty baryons and their antimatter versions decay. But here, the plot thickens. While the experiments proved the weapon, CP violation, is real, they also revealed a huge problem. When you add up all the known sources of this violation in the standard model of particle physics, the number is far, far too small to explain the universe we see. It's like finding a penknife at a crime scene that required a cannon. We've found *A glitch, but it's not the right one. This has forced physicists to look for a new, more powerful source of asymmetry. And a prime suspect has emerged, the neutrino. Neutrinos are the ghosts of the particle world. Billions are passing through you every second, yet they barely interact with anything. For decades, we thought they were massless. Then came a revolutionary discovery. Neutrinos oscillate, changing between 3 different flavors as they travel. This is only possible if they have mass, a discovery that broke the original standard model. This led to a tantalizing new theory, leptogenesis. Maybe the imbalance didn't start with quarks and baryons at all. Maybe it began with their lighter cousins, the leptons, the family of electrons and neutrinos. The theory goes, what if neutrinos and antineutrinos oscillate at different rates? This would be a form of CP violation among leptons. In the early universe, this could have created a surplus of leptons over antileptons, which other exotic processes then converted into the matter surplus we see today. The hunt has now shifted from colliders to colossal detectors buried deep underground. Two major experiments are leading the charge: the T2K experiment in Japan and the NOVA experiment in the US. They fire intense beams of neutrinos through hundreds of kilometers of solid rock and count how many change flavor. Then they do it all again with antineutrinos and compare. And the results have been electrifying. In 2020, T2K published data showing strong hints of a large asymmetry. Their results disfavored a symmetric universe at a 99.7% confidence level, suggesting neutrinos and antineutrinos do behave differently. While it's not yet the gold standard for a discovery, two independent experiments are pointing to the same exciting conclusion. To get a final answer, we need more power. And the next generation of neutrino hunters are being built right now. In the US, the Deep Underground Neutrino Experiment, DUNE, will send the world's most intense neutrino beam 1,300 kilometers from Illinois to giant detectors a mile underground in South Dakota. Meanwhile, Japan is building the Hyper-Kamiokande experiment, a truly colossal detector holding 250,000 tons of ultra-pure water, set to start up around 2027. These two mega-experiments are designed to settle the question once and for all. Within the next decade, we hope to finally know if neutrinos are the ultimate source of our existence. This search for the glitch is one of the most profound quests in science, and it's happening in real time. The answer to why we exist may be hidden in the subtle flicker of a ghostly particle. So what do you think? Is it some undiscovered feature of quarks, the weird dance of neutrinos, or something else entirely? Let us know in the comments. And if you enjoy exploring these cosmic mysteries, make sure to subscribe and ring that notification bell, so you don't miss our next journey to the edge of what we know. Conclusion: we started with a paradox. The laws of physics demand a perfect symmetry that should have left the universe a cold, empty void. Instead, we live in a cosmos teeming with galaxies, stars, and planets. A universe full of stuff. Our journey to solve this has taken us from the first instant of the Big Bang to the heart of particle colliders and deep into underground labs, all hunting for proof of this life-giving imperfection. What we've found is that the glitch is real. The universe is not perfectly symmetrical. The laws of nature do not treat matter and antimatter as perfect mirror images. This tiny, almost imperceptible flaw isn't a mistake. It's the most important feature of our universe. Without it, there would be nothing. Our existence is a celebration of imperfection. The beauty and complexity of the cosmos emerge not from flawless symmetry, but from the breaking of it. And this isn't just some abstract story. It's the most personal story there is. That 1 in a billion survival rate isn't just a number. It's you. Look at your hand. Feel your heartbeat. Every single atom in your body, the carbon, the oxygen, the hydrogen, is a direct descendant of one of those primordial survivors that escaped the Great Annihilation. You are the embodiment of the glitch. You are living, breathing proof that the universe broke its own rules. The final chapter is still being written. We have compelling suspects, but the case isn't closed. Explaining our own origin remains one of the greatest challenges in physics. But the fact that we can even ask this question, that we can build these incredible machines to listen to the whispers of the Big Bang, is perhaps the most amazing part of this entire improbable story. We are the children of a statistical anomaly, looking back and trying to understand the lucky break that allowed us to be. The universe's first microsecond was a total failure. What if the Big Bang was a dud? What if, for the first crucial moment of its existence, the universe was a total failure, actively working against the creation of reality? Before a single atom, before the first star could shine, before even the most basic building blocks of matter could get a foothold, the cosmos was a raging, chaotic inferno. It wasn't just empty, it was a state of being that furiously unmade itself, instant by agonizing instant. For about 1 microsecond, 1/1,000,000th of a second, the universe was a cosmic blender of pure, raw energy. A state of matter so extreme, so violent, that it refused to build anything. This was the quark-gluon plasma, a perfect, frictionless liquid of primordial chaos that held the potential for everything we see today but seemed hell-bent on making sure none of it ever existed. This is the story of how reality almost didn't happen. It's the story of the universe's first, most profound failure, and how that failure became its ultimate success. The blueprint for a failed universe. To understand this failure, we have to rewind the clock. Way back, not to the dawn of humanity, or even the birth of Earth, but to a time before time as we know it had any real meaning. We're going to the first trillionth of a second after the Big Bang. At this instant, the universe is unbelievably small, hot, and dense. The entire observable universe, with all its billions of light years, is crammed into a space no bigger than a grain of sugar. But this sugar cube holds the energy of everything. And the temperature is mind-boggling, hotter than the 2 trillion Kelvin it will cool to just a microsecond later. For comparison, the core of our sun is a mere 15 million degrees. This heat is so intense that the very ideas of matter and structure simply fall apart. In our world, everything is made of atoms. Atoms have a nucleus, with protons and neutrons, orbited by electrons. Those protons and neutrons are made of even smaller particles called quarks, which are held together by particles called gluons. Gluons are the carriers of the strong nuclear force, the most powerful force there is. Think of them as cosmic superglue. It's this glue that binds quarks into the trios that form protons and neutrons. And it's so strong that in our cool, modern universe, a single quark has never been seen on its own. They are permanently locked up inside larger particles. But in the furnace of the first microsecond, the universe is just too hot for this cosmic glue to work. The thermal energy is so overwhelming that it shatters the strong force's grip. It's like trying to build a delicate snowflake inside a volcano. Every time a few quarks get close and a gluon tries to bind them, the sheer violence of the environment blasts them apart again. The gluons can't hold on. The quarks can't be contained. This is the state known as the quark-gluon plasma, or QGP. It's a seething, turbulent soup where the fundamental building blocks of matter are deconfined and roam free. Quarks, anti-quarks, and the gluons that should be binding them are instead a chaotic swarm, zipping around at nearly the speed of light and smashing into each other trillions upon trillions of times a second. And this isn't just a wild theory, it's a state of matter we've actually recreated right here on Earth for tiny fractions of a second. At places like the Large Hadron Collider, LHC, at CERN and the Relativistic Heavy Ion Collider, RHIC, at Brookhaven National Laboratory, scientists accelerate heavy ions, like gold or lead atoms, to 99.999999% of the speed of light. They smash these ions together, creating collisions so energetic that for a split second, the temperature and pressure mimic the conditions of the early universe. In that moment, the protons and neutrons in the ions literally melt, releasing their quarks and gluons into a tiny, fleeting droplet of primordial soup. What they've discovered is stunning. This quark-gluon plasma doesn't act like a gas, with particles flying around randomly, as was once thought. Instead, it moves like a perfect, frictionless liquid. The quarks and gluons flow together, like a school of fish or a wave in the ocean. This shows that the QGP is an incredibly dense, strongly interacting medium, a single, unified, chaotic entity. This is the very definition of the universe's early failure. For those first critical moments, the cosmos was stuck in this liquid state of pure potential, but zero progress. It was a factory full of raw materials with a busted assembly line. The particles were all there, but the forces were powerless to build anything that could last. The universe was a frantic, seething ocean of almosts. The dance of creation and annihilation. To really get a feel for this chaos, we need to zoom in. The quark-gluon plasma wasn't just a demolition derby. It was a relentless cycle of creation and destruction. All thanks to the most famous equation in physics. E=mc². This equation tells us that energy and mass are two sides of the same coin. With enough energy, you can create matter. And the early universe was flooded with energy. High-energy particles of light, photons, were ricocheting everywhere like gamma-ray bullets. When two of these photons collided with enough force, their energy would spontaneously transform into a pair of particles. One matter particle and its twin, an antimatter particle. An up quark and an anti-up quark would just blink into existence out of pure energy. But this creation was instantly matched by destruction. When a matter particle meets its antimatter twin, they annihilate each other, disappearing in a flash of energy that releases more high-energy photons. So, for that first microsecond, the universe was trapped in a furious, perfectly balanced dance. Photons collide, creating a quark and an anti-quark. The quark zips off, travels a microscopic distance, and inevitably slams into another anti-quark. They annihilate, creating new photons. Those photons then fly off and create yet another pair of particles. On and on it went. A pointless, cosmic recycling program. Matter was being born and erased trillions of times a second. For every particle created, another was destroyed. No net gain, no progress. The universe was furiously running in place, generating and then destroying the very building blocks of reality. It was a state of perfect, maddening equilibrium. This brings us to one of the biggest unsolved mysteries in physics: the matter-antimatter asymmetry problem. According to our best theories, the Big Bang should have created matter and antimatter in exactly equal amounts. If that had happened, as the universe expanded and cooled, every single particle would have found a partner and annihilated. The result? A universe filled with nothing but a faint, boring glow of light. No stars, no galaxies, no planets, and no one to wonder why. And yet, here we are. You, the Earth, the Sun, it's all matter. For some reason, that perfect symmetry was broken. The dance of creation and annihilation somehow ended with a tiny, almost insignificant surplus of matter. The leading idea is that for every billion pairs of matter and antimatter particles, there was just one extra matter particle. 1 in a billion. When the annihilation frenzy ended, that tiny leftover fraction of matter is what remained. And that fraction became everything. What caused this life-saving imbalance? We don't know for sure, but a huge piece of the puzzle is something called CP violation, or charge parity violation. Put simply, it means the laws of physics might not apply to matter and antimatter in exactly the same way. While the conditions for this asymmetry were likely set even before the quark-gluon plasma existed, during the preceding electroweak epoch, the QGP was the chaotic battlefield where the consequences played out. Experiments have shown that some particles and their antiparticles decay at slightly different rates. It's a subtle but profound asymmetry. This tiny bias, playing out over countless trillions of interactions in the primordial soup, may have been just enough to tip the scales, ensuring a 1 in a billion surplus of matter survived. The chaos wasn't just destructive, it was the stage for a grand cosmic heist, where matter stole a tiny advantage to guarantee its own future. How we know what we know. This story of a multi-trillion degree primordial soup might sound like science fiction. How can we possibly know what the universe was like in its first millionth of a second? The answer is that we've become cosmic time travelers. Not with a time machine, but by building machines that can recreate the universe's most extreme conditions right here on Earth. These machines are particle accelerators, the most powerful scientific instruments ever built. The most famous is the Large Hadron Collider, or LHC, at CERN. The LHC is a 27-kilometer ring of superconducting magnets buried underground, where beams of particles, often lead ions, are accelerated in opposite directions to 99.999999% of the speed of light. When these beams are smashed together head-on, their energy is released in a microscopic fireball. For less than a trillionth of a second, the temperature and density inside that fireball replicate the conditions of the quark-gluon plasma. The collision is so hot it melts the protons and neutrons themselves, dissolving them into their basic components. For a brief moment, a droplet of QGP exists inside a detector. Surrounding the collision point are detectors the size of apartment buildings, like Atlas and CMS. These are basically giant, 3D digital cameras, layered with electronics designed to track every single particle that flies out of the fireball. They can't see the QGP directly because it vanishes almost instantly. Instead, scientists act like cosmic detectives, studying the debris from the crash to figure out what happened. By analyzing the thousands of particles that spray out, they can piece together the properties of the plasma that created them. One of the key clues they look for is a phenomenon called jet quenching. Imagine two quarks hitting each other. In a simple collision, they'd fly off in opposite directions, creating two narrow jets of particles. But in a heavy ion collision where a QGP is formed, something different happens. If a pair of quarks is created near the edge of the plasma, one quark might escape cleanly, forming a powerful jet. But the other quark, trying to fly through the entire droplet of super-dense plasma, loses energy, like a bullet fired into water. Its jet gets quenched. By measuring the energy difference between the two jets, scientists can calculate just how dense and interactive the QGP is. It's this kind of measurement that confirmed the QGP behaves like a perfect liquid, not a gas. So when we talk about the quark-gluon plasma, we're not just guessing. We are describing a state of matter that has been created, measured, and studied in labs. Every detail we learn is another clue connecting us back across 13.8 billion years of history, allowing us to verify the story of the universe's first, most chaotic moments. The Great Thaw. Reality's winning moment. For about a microsecond, the universe was stuck in a loop. A hot, dense, liquid plasma of free quarks and gluons, where lasting structure was impossible. But the universe had a built-in escape plan: expansion. From the very first instant, the universe was expanding. And as it expanded, it cooled. It's the same reason a can of compressed air feels cold when you spray it. The expanding gas drops in temperature. For the universe, this cooling was relentless. As the cosmic clock ticked past the 1 microsecond mark, the universe crossed a critical threshold. The temperature dropped to just below that magic number of about 2 trillion Kelvin. This might not sound like a huge change, but for the fundamental forces, it was everything. At this slightly cooler temperature, the violent energy of the particles was no longer enough to overcome the binding power of the strong nuclear force. Suddenly, the gluons could finally do their job. This moment is known as hadronization, or the Great Confinement. It was a phase transition as dramatic as liquid water freezing into solid ice. All across the cosmos, at the same time, the rules changed. Imagine the scene. Two quarks fly past each other. A moment before, they would have been instantly knocked apart. But now, as a gluon forms a bond between them, the bond holds. The surrounding energy can no longer break it. The quarks are trapped. They are confined. Quarks have to bundle together in specific, neutral combinations. So, a quark and an antiquark bind together to form a meson. Or, three quarks bind together to form a baryon. And just like that, the first stable, composite particles of matter were born. Protons, two up quarks and a down quark. Neutrons, one up quark and two down quarks. These are the hadrons that give this new era its name. The chaotic free-for-all of the quark-gluon plasma was over. The reign of hadrons had begun. This was the turning point. The universe had finally succeeded. It had taken the raw, untamed potential of the QGP and forged it into the first recognizable, stable building blocks of matter. The assembly line was finally working. The universe was still an incredibly hostile, trillion-degree soup of particles, but crucially, protons and neutrons were now stable. They could survive the inferno. This transition from a deconfined plasma to a gas of hadrons was the climax of the universe's origin story. It was the moment the failure ended. Without it, the story would have stopped right there. The universe would have just remained a homogeneous, uninteresting soup of free particles, expanding and cooling forever with nothing to show for it. Conclusion: the necessary failure. The story of the universe's first microsecond seems, at first glance, like a story of total failure. A failure to build, to progress, to create anything that could last. The universe began not with a triumphant march, but with a chaotic, self-destructive temper tantrum. But as we've seen, this initial failure wasn't just a prologue to the real story, it was the story. The chaos of the quark-gluon plasma was a necessary crucible. It was the arena where the slight matter-antimatter imbalance, likely established moments before, allowed matter to win its existential duel. Had the universe been more orderly from the start, it might have been perfectly symmetrical, and therefore, perfectly empty today. The failure of the strong force to bind quarks was temporary. But it was in that brief window of failure that the universe secured its future, ensuring there would be something left to build with when the time was right. Then came the turning point, the Great Confinement. As the universe cooled, the failure ended. The strong force took hold, binding quarks into the first protons and neutrons. It was the universe's declaration that the era of destruction was over, and the era of construction had begun. From these first simple particles, the story of cosmic evolution could finally begin. Over the next few minutes, they would fuse into the first atomic nuclei. For 380,000 years, the universe would remain an opaque plasma, until it cooled enough for atoms to form, releasing the light we now see as the cosmic microwave background. And from those first clouds of gas, gravity would sculpt the first stars and galaxies, lighting up the cosmos and beginning the long, slow process that would eventually lead to us. So, was the first microsecond a failure? Absolutely. It failed to make a single stable proton. It failed to create a single atom. But it was the most important failure in the history of everything. It was a necessary chaos, a destructive dance that, through a subtle imperfection, left behind the seeds of all creation. Our existence is a direct result of that primordial failure. We are the leftovers of a cosmic war, built from the ashes of a time when the universe itself couldn't hold it together. The story of our origins isn't one of flawless design, but of a chaotic, imperfect, and ultimately triumphant struggle against non-existence. If you're fascinated by the raw, untamed power of the early universe and want to see more deep dives like this, consider supporting us on Patreon. Your support helps us explore the biggest questions in science. And for more journeys into the fabric of reality, from the infinitely small to the infinitely large, make sure you subscribe and hit the bell so you don't miss what's next. Thanks for watching. The 3 minutes that built our entire universe. Imagine we could rewind time. Not just a few years, but the whole 13.8 billion year story of our universe. We fly backwards, past galaxies and the birth of our own sun, past the very first stars that lit up the cosmic dark. We keep going, rewinding through millions of years of blackness, all the way back to a moment of unimaginable beginning. A point so hot and dense that the entire universe was smaller than an atom, and the laws of physics were still being written. We're going to the most critical moment in the history of reality. A period so brief, yet so important, that the fate of everything, every star, planet, and person, was decided in less time than it takes to make a cup of tea. We are going to the first 3 minutes. This is the story of how our universe almost didn't happen. A cosmic balancing act so precise that one tiny misstep would have left a universe of nothing. A silent, empty cosmos filled with useless radiation. So, what exactly happened in those first 180 seconds that built the foundation of everything we see and everything we are? The first picture, setting the stage. To understand the first 3 minutes, we have to start even earlier, in the first fraction of a second. Here, the universe is a quark-gluon plasma, a state of matter so extreme that protons and neutrons haven't even formed yet. It's a perfect, chaotic soup of fundamental particles and pure energy. But right away, the universe faced its first great test. The laws of physics are beautifully symmetric. They predict that when energy creates a particle of matter, it must also create an equal and opposite particle of antimatter. When these two meet, they annihilate each other in a flash of energy, leaving nothing behind. The Big Bang should have created matter and antimatter in perfect balance. For every quark, an anti-quark. For every electron, a positron. In a perfectly symmetrical universe, as this soup cooled, every particle would have found its anti-particle twin, and the entire cosmos would have wiped itself out, becoming a vast, empty sea of light. No substance, no structure, no future. But that's not what happened. For a reason scientists are still trying to figure out, the rules were broken. A tiny imbalance was introduced. For every billion pairs of matter and antimatter particles, the universe somehow made one extra particle of matter. Just 1 in a billion. That tiny leftover scrap is the only reason you exist. After all the annihilation was over, that little bit of matter was all that was left, the seed of our entire reality. Every galaxy, star, and atom in your body is made from the leftovers of that first, miraculous imbalance, a mystery we call baryogenesis. It's the event that guaranteed there would be a universe at all. As this surviving soup of particles and energy kept expanding and cooling, the chaos began to settle. The universe was about to take its first real step toward building something. The clock was ticking toward 1 second, the moment our story truly begins. The clock starts, the first second. Time marker. T plus 1 second. Temperature marker. 10 billion degrees Kelvin. At the 1 second mark, the universe has cooled just enough for the quarks, which had been swimming freely, to grab each other in groups of 3. For the first time, we see the birth of familiar particles, protons and neutrons. These are the building blocks of every atom that will ever exist. Let's meet our 2 main characters. On one side, the proton. It's positively charged and incredibly stable. A proton can last for trillions of years. On the other side, we have the neutron. It has no charge, is slightly heavier, and has a fatal flaw: it's unstable. A free neutron, left on its own, will decay into a proton in about 10 minutes. This means that after 10 minutes, half the free neutrons are gone. After an hour, they practically all vanished. This instability is a ticking clock for the universe. There's a limited supply of neutrons, and if the cosmos doesn't use them fast, they'll disappear, leaving behind a universe of only protons. So why don't they just stick together now? The temperature. At 10 billion degrees, the universe is a furnace filled with high-energy photons, particles of light, that act like a demolition crew. A proton and a neutron might try to fuse into a simple nucleus called deuterium, 1 proton, 1 neutron. But the instant they do, a powerful gamma-ray photon smashes them apart again. It's a cosmic dance of 2 steps forward, 2 steps back. This problem is called the deuterium bottleneck. The universe is stuck. It has the parts to build atoms but is too hot for them to stay together. It's like trying to build a sandcastle in a hurricane. And all the while, that ticking clock is getting louder. Neutrons are decaying. At this stage, for every 1 neutron, there are already about 6 protons. If the universe stays this hot for just a few more minutes, all the neutrons will be gone. Imagine that for a second. If the universe failed here, we'd have a cosmos made of only protons, the nuclei of hydrogen atoms. A universe of 100% hydrogen. While our universe is mostly hydrogen, it's the other stuff that makes stars work the way they do. Without neutrons, there's no helium from the Big Bang. Without primordial helium, the first stars would have been completely different, likely leading to a much emptier, darker universe. The first rung on the ladder of complexity would have been missed. The window opens, breaking the bottleneck. The universe's saving grace is its relentless expansion. As space stretches, the energy thins out, and the temperature plummets by billions of degrees every second. Time marker. T plus 2 minutes. Temperature marker. Approximately 1.2 billion Kelvin. As the clock ticks past 2 minutes, the universe crosses a magical line. The photons zipping around no longer have enough energy to instantly shatter every deuterium nucleus. The deuterium bottleneck is broken. This triggers a furious chain reaction. For the first time, a proton and a neutron can fuse and survive. P plus N right pointing arrow deuterium. In the dense cosmic soup, this new deuterium nucleus immediately finds another particle to react with. The universe's first element factory roars to life. A deuterium nucleus can hit a proton, forming helium-3. Deuterium plus P right pointing arrow helium-3. Or, it can hit a neutron, forming tritium. Deuterium plus N right pointing arrow tritium. Both are crucial stepping stones. They exist just long enough to take part in the final, most important reaction, which leads to the grand prize, helium-4. Helium-4 has 2 protons and 2 neutrons, and its nucleus is a fortress, one of the most stable configurations in physics. Once formed, it's incredibly hard to break apart. So, the moment the bottleneck broke, the universe began an almost complete conversion of its available neutrons into helium-4. Every free neutron was rapidly captured and locked safely inside a helium nucleus, where it becomes stable. The ticking clock of neutron decay was silenced just in the nick of time. This wasn't a gradual process. It was a dam breaking. In just over a minute, nearly all the free neutrons in the universe were consumed and fused into helium. From a chaotic mess of particles, the universe had forged the second most abundant element in existence. But the same cooling that opened this window of opportunity was about to slam it shut. The window closes, the 3-minute mark. The frenzy of creation is intense, but it can't last. The universe is still expanding and cooling, which creates one final problem. Time marker. T plus 3 minutes. Temperature marker. 1 billion Kelvin. By the 3-minute mark, the temperature has dropped to a mere 1 billion degrees. For nuclear fusion, that's getting chilly. Particles are now moving more slowly, and a fundamental force of nature starts to win: electrostatic repulsion. Protons and nuclei are all positively charged, and like magnets, they push each other away. To fuse, particles need to slam into each other with incredible speed, which requires heat. As the temperature drops, fewer and fewer particles have enough energy to overcome this repulsion. Fusion becomes rare. The universe is also getting less dense, so collisions happen less often. The cosmic element factory is shutting down. The window that opened so dramatically is now closing. By the time the universe is 20 minutes old, the temperature and density will have fallen so low that nuclear fusion stops completely. Big Bang nucleosynthesis is over. So what's the result? When the dust settles, the composition of the universe is fixed. By mass, the cosmos is now roughly 75% hydrogen nuclei and 25% helium-4 nuclei. There are also tiny traces of deuterium and lithium, but almost everything is hydrogen and helium. This reveals the profound truth of the first 3 minutes. Our universe exists on a knife's edge. It needed a Goldilocks cooling rate, not too fast, not too slow, to produce the exact mix of hydrogen and helium that would fuel the first stars. The recipe for the cosmos was written, and for the next 380,000 years, the universe would simply expand and cool in darkness, a vast, opaque cloud of hot plasma. We've just built the raw ingredients of the cosmos. The hydrogen and helium from these 3 minutes are the seeds for everything that comes next. But how do you get from a uniform gas cloud to the brilliant complexity of stars and galaxies? That's a story for another time. But first, how can we be so sure any of this incredible 3-minute story is actually true? The proof: echoes of the beginning. This whole story might sound like science fiction. We can't go back 13.8 billion years to check. So how do we have any confidence in it? The answer is that this theory, Big Bang nucleosynthesis, BBN, makes concrete, testable predictions. It's not just a story. It's a mathematical model based on the laws of nuclear physics. As explained in Steven Weinberg's classic 1977 book, The First 3 Minutes, if you apply known physics to the conditions of the hot, early universe, you can calculate exactly what it should have created. The model's biggest prediction is about the abundance of light elements. It calculates that after the first few minutes, ordinary matter should be about 75% hydrogen and 25% helium by mass. To test this, astronomers look at the most ancient and pristine places in the cosmos, distant gas clouds that have been floating undisturbed for billions of years, or the oldest stars in our galaxy. These are places that haven't been polluted by heavier elements made in later stars. And when they measure the composition of this ancient material, they find the same thing over and over. A universe that is about 75% hydrogen and 25% helium. This stunning agreement between a theoretical prediction and observational data is one of the pillars of modern cosmology. Couldn't stars have just made all that helium? No. Stars do fuse hydrogen into helium, but they do it slowly, and most of that helium stays locked inside them. Even after billions of years, stars haven't made nearly enough helium to account for the 25% we see everywhere. That much helium had to be created all at once, everywhere, very early on. BBN is the only explanation that fits. There's another line of evidence, from about 380,000 years after the Big Bang. This was the moment the universe finally cooled enough for electrons to combine with nuclei to form the first neutral atoms. The universe, once an opaque fog, suddenly became transparent. The light that was present at that exact moment was set free, and it has been traveling across the cosmos ever since. Today, we detect that ancient light as the cosmic microwave background, CMB, a faint glow of radiation filling the entire sky. The CMB is literally the afterglow of the Big Bang, a baby picture of the universe. Its properties confirm that the early universe was indeed incredibly hot and dense, just as the BBN model requires. The physics of the first 3 minutes predicts the fuel, and the CMB shows us the fire. Conclusion: in just 180 seconds, the universe went from a featureless, chaotic inferno to a cosmos with a fixed chemical recipe. It survived the threat of annihilation by antimatter, a bottleneck that almost prevented any construction, and a ticking clock of decaying neutrons. It survived because of a cooling rate so perfectly balanced it seems almost impossible. The result was a universe of hydrogen and helium, the raw materials for everything to come. This primordial gas would collapse to form the first stars. In their explosive deaths, those stars would forge the heavier elements the Big Bang could not: the carbon in our DNA, the oxygen we breathe, and the iron in our blood. But those stars could only exist because the first 3 minutes gave them fuel to burn. Without the vast reserves of hydrogen and that crucial 25% helium, the story of stars, galaxies, and us could never have begun. The entire 13.8 billion-year epic of cosmic history was made possible by the events of its first 3 minutes. Every time you look at the night sky, you're seeing the direct consequence of that brief, violent, and impossibly precise moment. Our own story began, and was almost over, in the first 3 minutes. If you find the story of our universe as fascinating as we do, subscribe and hit the bell so you don't miss our next journey into the cosmos. And check out this video next to see what happened in the billion years after the first 3 minutes, as the universe entered the Dark Ages and began the slow, patient work of building the first galaxies. The physics paradox that almost made reality impossible. Classical physics, the beautiful, elegant set of laws that govern our everyday reality, had a terrifying secret. Buried deep inside its most foundational equations was a catastrophic flaw. It was a flaw that predicted that every single object in the universe, the chair you're sitting on, the phone in your hand, the very stars in the night sky, should instantly and violently erupt with an infinite amount of energy. This wasn't some minor miscalculation. It was a prediction that everything, everywhere, should already have vaporized in a single, blinding flash of high-frequency light. This spectacular failure of science became known as the ultraviolet catastrophe. The fact that we are here, that you and I exist at all, was undeniable proof that the very pillars of physics were fundamentally wrong. Solving this wouldn't just patch a hole in a theory, it would force a complete reinvention of science and our concept of what's real, giving birth to the strange, bewildering, and powerful world of quantum mechanics. This is the story of how a simple glowing ember exposed a crack in the fabric of reality, and how one physicist's act of desperation saved us all from an imaginary, yet theoretically certain, doom. The Gilded Age of Physics. To really feel the depth of this crisis, we had to travel back to the end of the 19th century. This was a time of immense confidence, a kind of Gilded Age for physics. For over 200 years, the laws laid down by Isaac Newton had reigned supreme. His mechanics could predict the arc of a cannonball and the orbit of a planet with breathtaking precision. It seemed like the universe was just a grand, cosmic clockwork, and humanity had finally found the instruction manual. That confidence was supercharged in the 1860s and 70s by James Clerk Maxwell. In what is still one of the greatest triumphs of theoretical science, Maxwell unified the seemingly separate forces of electricity, magnetism, and light into a single, elegant framework: the theory of electromagnetism. His equations described light as a wave, a ripple in an invisible electromagnetic field, and they traveled at a constant, unchangeable speed. It felt like the final pieces of the puzzle were clicking into place. According to this classical view, the universe was deterministic. If you could know the exact position and momentum of every particle in existence, you could, in principle, calculate the entire future and reconstruct the entire past. Everything was cause and effect, a perfect, predictable machine. There was a real sense that the grand project of physics was nearing its end. All that was left was to fill in the details. This feeling was famously captured in a 1900 speech by the brilliant and highly respected physicist Lord Kelvin. He declared that the sky of physics was almost perfectly clear, except for two small, troublesome clouds on the horizon. The first cloud was the baffling result of the Michelson-Morley experiment, which had tried and failed to detect the luminiferous ether, a hypothetical substance physicists believed light waves had to travel through. That failure would eventually lead Albert Einstein to his theory of special relativity, completely changing our ideas of space and time. But that's a story for another day. The second cloud, the one that concerns us, seemed much more obscure. It was a problem related to how energy is shared among vibrating particles, known as the Maxwell-Boltzmann doctrine on the equipartition of energy. At the time, it looked like a niche problem. Few could have predicted that this second cloud wasn't a cloud at all, but the leading edge of a hurricane, a storm that wouldn't just obscure the sky of physics, but tear it completely apart. The problem that spawned this storm was, on the surface, incredibly simple. Why does a hot object glow? The crack in the foundation, a simple glowing ember. Think of a blacksmith pulling a piece of iron from a forge. It glows a deep, cherry red. As it gets hotter, the color shifts to bright orange, then to a brilliant yellow-white. Or just think about the heating element of an electric stove, which goes from black to a dull red as it heats up. This phenomenon, the light emitted by any object just because it's hot, is known as thermal radiation. For centuries, it was a familiar, everyday thing. But for the physicists of the late 19th century, it became a source of deep frustration. They wanted a single, universal law that could predict the exact spectrum of light, the precise mix of colors and their intensities, that an object would emit at any given temperature. To make the problem simpler, they imagined an idealized object they called a blackbody. A blackbody is a perfect absorber and emitter of radiation. Any light that hits it gets completely absorbed, not reflected, and it emits radiation in a way that depends only on its temperature, not what it's made of. Now, a perfect blackbody doesn't exist in nature, but you can make a really good one. Just take an enclosed box, like an oven, and poke a tiny hole in it. Any light that goes into the hole will bounce around, get absorbed by the walls, and have almost no chance of getting back out. That tiny hole, then, acts like a perfect absorber. So, if you heat the oven, the light streaming out of the hole is a near-perfect sample of blackbody radiation. Experimental physicists in Germany, with their legendary precision, did exactly this. They built sophisticated cavities, heated them to exact temperatures, and used sensitive instruments to measure the spectrum of light that was emitted. And they found a beautifully consistent pattern. For any given temperature, the radiation curve would start low in the infrared and red part of the spectrum. It would then rise to a peak intensity at a specific color, and then, crucially, it would fall off again, dropping back down to zero in the violet and ultraviolet part of the spectrum. As the temperature went up, the light got more intense, and that peak shifted towards higher frequencies, from red to orange to yellow. The experimental data was clear and repeatable. The challenge was to explain it with the physics they already had. And this is where the trouble began. The first major attempt came from a German physicist named Wilhelm Wien. His formula worked great for the high-frequency part of the spectrum, where the curve falls off, but it failed at lower frequencies. Then, two brilliant physicists, Lord Rayleigh and Sir James Jeans, tackled the problem from the ground up, using principles they thought were absolutely unshakable. Maxwell's theory of electromagnetism and a core concept from thermodynamics called the equipartition theorem. Their result, which became known as the Rayleigh-Jeans law, was supposed to be the final word. It was supposed to be a triumphant confirmation of classical physics. Instead, it was a disaster. The Rayleigh-Jeans law perfectly matched the data, but only at the very low frequency end of the spectrum. As the frequency increased, their predictions started to stray from reality. And at the high frequency end, the blue, violet, and especially the ultraviolet, it didn't just stray, it went completely, catastrophically wrong. Where the real-world measurements showed the energy dropping back to zero, the Rayleigh-Jeans law predicted it would shoot upwards, straight towards infinity. This wasn't a small error. It was a fundamental breakdown of their theory. It was the paradox that would earn the name, the ultraviolet catastrophe. The catastrophe unveiled. So why did the most trusted laws of physics predict something so insane? To get it, we need to look inside that idealized oven the way Rayleigh and Jeans did. According to Maxwell's theory, the light inside this box exists as electromagnetic waves. But because they're trapped, they can't just have any random shape. They have to exist as standing waves, just like the vibrations on a guitar string. A guitar string is fixed at both ends, so it can only vibrate in specific patterns or modes. It can vibrate as one big arc, its fundamental frequency, as two arcs, as three, and so on. Each of these modes has a specific wavelength. Rayleigh and Jeans figured the light inside the cavity must be the same. The light is just a collection of standing waves, each one a distinct mode of vibration with its own frequency. You've got modes for infrared light, modes for red light, green light, and so on, all the way up the spectrum. So far, so good. The next step was to figure out how the oven's thermal energy was distributed among all those different modes. For this, they turned to a cornerstone of classical thermodynamics, the equipartition theorem. The theorem is basically a democratic principle for energy. It says that for a system in thermal equilibrium, every independent way a system can hold energy, every degree of freedom, gets an equal, average share of the total energy. That tiny share is known as kT, where K is a number called the Boltzmann constant and T is the temperature. Rayleigh and Jeans treated each standing wave mode as one of those degrees of freedom. So, according to the equipartition theorem, every single mode of vibration, no matter its frequency, should have the same average energy, kT. And with that one, simple, logical step, the catastrophe was born. Think about the guitar string again. You can have a mode with one arc, 2, 3, 4, a whole lot. The same is true for the light waves in the box. There are some modes for low frequencies. Then there are more available modes for slightly higher frequencies. And even more for still higher ones. Here's the fatal flaw. As you go to shorter and shorter wavelengths, higher and higher frequencies, into the ultraviolet and beyond, the number of possible standing wave modes that can fit inside the box just keeps going up. There's no upper limit. Mathematically, there are an infinite number of possible modes. Now, combine that with the equipartition theorem. If there are infinite modes, and every single one must contain an average energy of kT, then the total energy inside the box has to be infinite. Infinite modes times even a tiny bit of energy per mode equals infinite energy. That's the mathematical core of the ultraviolet catastrophe. The theory predicted that any object with any temperature above absolute zero should be a runaway fountain of infinite energy, blasting out an impossible amount of radiation, mostly in the ultraviolet, X-ray, and gamma-ray frequencies. The implications were just terrifying. If the Rayleigh-Jeans law were correct, our universe couldn't exist. The moment you lit a candle, it should release infinite energy and vaporize the room. A simple cup of warm tea should be more destructive than a supernova. Our own bodies, warm and radiating, should be erupting with a cataclysmic, world-ending torrent of high-frequency radiation. But they don't. The universe is stable. Reality is not instantly vaporizing. The experimental curves clearly showed the energy tapering off to zero. Physics was broken. The elegant, clockwork universe of Newton and Maxwell had produced a prediction that wasn't just wrong, but absurdly, fundamentally, existentially wrong. The stage was set for a revolution, and the hero of our story was a man who had no intention of starting one. The reluctant revolutionary, Max Planck. Enter Max Planck. Born in 1858, Planck was the very model of a late 19th century German physicist, conservative, methodical, and deeply respectful of the established laws. He wasn't some young radical looking to tear everything down. In fact, he was a master of thermodynamics, and he had dedicated his life's work to proving that its laws were absolute. Planck became obsessed with the blackbody problem. He wasn't motivated by the absurdity of the catastrophe, that name came years later. He was driven by a theorist's pure desire to find a single, beautiful equation that could perfectly describe the experimental data. His first big step, in October of 1900, was basically a clever mathematical trick. He took the two existing formulas, Wien's law, which worked for high frequencies, and the Rayleigh-Jeans law, which worked for low ones, and he found a way to stitch them together. He created a new hybrid formula that, to his delight, fit the experimental data perfectly across the entire spectrum. But for a mind like Planck's, that wasn't enough. An equation that just works without a physical reason why it works isn't physics, it's just a neat trick. Planck had to find a proper theoretical derivation for his formula. He had to build it from the fundamental principles of thermodynamics and electromagnetism. He spent the next 2 months in what he later called, the most strenuous work of my life. He tried everything within the rules of classical physics. He modeled the oven walls as being lined with tiny oscillators, think of them as microscopic vibrating springs, that absorbed and re-emitted the radiation. But every path he took led back to the same classical assumptions, and the same catastrophic failure. The infinite energy was an unavoidable consequence of a continuous world. Finally, backed into a corner, Planck decided to try something he didn't really believe. It was a move he later called an act of desperation. He was using a statistical approach from Ludwig Boltzmann, which involved counting the ways energy could be distributed. As a mathematical tool, Boltzmann would temporarily divide energy into discrete chunks to make the counting easier, before taking the limit of those chunks going to zero to get back to the smooth, continuous reality of the classical world. Planck's desperate idea was to ask, what if you just don't take that final step? What if energy isn't continuous? What if the oscillators in the walls couldn't absorb or emit just any old amount of energy? What if energy itself came in packets? He proposed that the energy of an oscillator could only exist in multiples of some fundamental unit. An oscillator could have 0 energy, or 1 unit, or 2 units, or 3, but absolutely nothing in between. It's like saying you can climb a staircase, standing on the first, second, or third step, but you're physically forbidden from hovering anywhere in between. More than that, Planck proposed that the size of this energy packet, which he called a quantum, from the Latin for how much, wasn't fixed. To make his formula work, he found that the size of the packet had to be proportional to the frequency of the light. A low-frequency oscillator could only emit small packets of energy. A high-frequency oscillator could only emit large packets of energy. He captured this relationship in one of science's most famous equations, E equals hf. Energy, E, equals a new fundamental constant of the universe, h, now called Planck's constant, multiplied by the frequency, f. With this radical, and frankly, unbelievable assumption, Planck went back to his calculations. And something magical happened. Slaying the infinite dragon, Planck's strange new rule, E equals hf, was the weapon that finally slew the infinite dragon of the ultraviolet catastrophe. The solution was as elegant as it was bizarre, and it came directly from his desperate assumption. Let's go back inside that oven one last time, with all its standing wave modes. Classical physics, with its democratic equipartition theorem, tried to give every mode an equal share of the energy. That worked fine for the low-frequency modes, because the energy cost to excite a long wavelength wave was tiny. There was plenty of thermal energy to go around. But Planck's new rule changed everything for the high-frequency modes. According to E equals hf, a mode with a very high frequency requires a very large chunk of energy just to get excited once. You can't give it a tiny bit of energy. You have to give it one whole, giant quantum, or nothing at all. Suddenly, the energy distribution wasn't so democratic anymore. It became a harsh, probability-based economy. The oven only has a finite amount of thermal energy to go around. And when the system tries to distribute that energy, it finds that for the extremely high frequency modes, the price of admission, that single quantum of energy, hf, is incredibly expensive. It becomes statistically very, very unlikely that any single mode will manage to randomly accumulate enough thermal energy to afford one of these enormous packets. Most of the energy gets distributed easily among the countless, cheap, low-frequency modes. The high-frequency modes, demanding their huge energy quanta, are effectively frozen out. They exist in theory, but they're almost never activated. Imagine a giant arcade where every machine gives a prize. The machines on the left cost 1 penny to play. The machines further to the right cost $1, then 10, then 1,000, then $1 million. If you let a crowd of people with a limited amount of pocket change loose, the penny machines will be going non-stop. The dollar machines will get some action. But that $1 million machine? It's almost certainly going to stay silent all day. No one can afford the entry fee. This is exactly what Planck's idea did to the energy spectrum. At low frequencies, his formula behaved just like the classical Rayleigh-Jeans law, matching the experiments perfectly. But as the frequency increased, the quantum cost started to kick in. The probability of a mode getting excited plummeted. The theoretical curve, instead of shooting to infinity, now gracefully peaked and then bent back down, heading straight for zero in the ultraviolet range, just like the real-world data. It was a perfect match. The infinity was gone. The catastrophe was averted. Planck had found the physical reasoning behind his equation. He'd solved the paradox. But he did it by shattering the continuous nature of energy, a core principle of physics for centuries. The dawn of a new reality. On December 14, 1900, Max Planck presented his derivation to the German Physical Society. This date is now widely seen as the birthday of quantum mechanics. But at the time, there were no fireworks. The revolution began not with a bang, but with a reluctant whisper. Planck himself was deeply unsettled by his own discovery. He thought of quantization as a mathematical trick, a calculational fix he had been forced to use. He spent years trying to find a way to absorb his quantum hypothesis back into the comfortable, continuous world of classical physics, but he never succeeded. The rest of the physics community was mostly skeptical. The idea was just too strange, too radical. For 5 years, the quantum was a curious but unproven idea. Then, in 1905, a young patent clerk in Bern, Switzerland named Albert Einstein published a series of world-changing papers. In one of them, Einstein took Planck's desperate act and declared it wasn't a trick at all. He argued that light itself was fundamentally quantized. Einstein proposed that light isn't a continuous wave, but a stream of actual, physical particles of energy, which we now call photons. He used this bold idea to explain another unsolved mystery, the photoelectric effect, where light knocks electrons out of a metal. He showed that the energy of those electrons depended on the light's frequency, its color, not its intensity, a perfect real-world confirmation of Planck's E equals hf. It was Einstein who really transformed Planck's reluctant hypothesis into a true physical reality. He kicked the door open, showing that the quantum world wasn't just a weird property of idealized ovens, but a fundamental feature of the entire universe. After that, the resistance began to crumble. In 1913, Niels Bohr used the quantum hypothesis to build a model of the atom that finally explained why atoms only emit light at specific frequencies, providing even more stunning evidence. The two clouds that Lord Kelvin had talked about in 1900 had, indeed, become storms. The first, about the ether, was swept away by Einstein's relativity. And the second, the one that spawned the ultraviolet catastrophe, had unleashed the far greater, and far stranger, storm of quantum mechanics. This journey from a perfect, clockwork universe to a bizarre, quantized one completely reinvented our understanding of matter, energy, and reality itself. If you enjoy untangling the biggest ideas in science, consider subscribing and joining our community of curious minds. And let us know in the comments, what other physics paradoxes should we explore next? The story of the ultraviolet catastrophe is a powerful testament to how science actually works. Its greatest leaps forward often begin not with a confident, "Eureka," but with a confused, "That can't be right." A terrifying flaw, a prediction that reality itself should fail, forced a generation of physicists to abandon centuries of certainty. Max Planck, a conservative physicist just trying to solve a puzzle about why things glow, was pushed into an act of desperation that accidentally became the first shot in a scientific revolution. He solved the paradox of infinite energy, but in doing so, he shattered the smooth, continuous world of classical physics. He revealed a new reality underneath, one that is grainy, probabilistic, and deeply weird. He opened a Pandora's box of questions we're still grappling with today. Why is the universe quantized? What does it mean for reality to be built on chance? The ultraviolet catastrophe was averted, but the mystery it uncovered is one we are still just beginning to understand. And it all started with the simple, beautiful, and paradoxical glow of a hot object. Why anything exists: the universe's ultimate switch. Consider a universe nearly identical to our own. It originates from a Big Bang and is composed of the same fundamental particles. In this alternate cosmos, however, a single, critical event in the first trillionth of a second does not occur. The result is a universe of pure, featureless energy, a cosmos of light and radiation, expanding and diluting into an empty continuity. No matter would form. No atoms, no stars, no planets, and consequently, no life. This scenario is not science fiction, but a real physical possibility. The existence of all matter, the substance of the world itself, appears to hinge on a single cosmic event: the moment matter was permitted to exist. This is the story of that mechanism, a process governed by a fundamental component of reality known as the Higgs field. It is an examination of how our universe transitioned from a state of pure energy to a state of substance, and the specific conditions that allowed this transition to happen. We will investigate the most significant picosecond in cosmic history to understand the event that allowed for the formation of structure, and explore the profoundly different alternate reality that our universe avoided. The primordial inferno. To understand this mechanism, we must first examine the state of the universe before it occurred. This requires us to go back to the first instant of creation. The time is 1 picosecond, 1 trillionth of a second, after the Big Bang. At this moment, the universe was a searing inferno of pure energy, hotter and denser than anything now conceivable. The temperature was approximately 10 to the power of 15 Kelvin, or 1 quadrillion degrees. The entire observable universe was compressed into a volume smaller than a grain of sand. Within this crucible, the fundamental constituents of reality existed in an indifferentiated state. These were the particles of the standard model of particle physics: quarks, electrons, and neutrinos. Quarks are the particles that would eventually combine to form protons and neutrons. Electrons are the particles that would orbit atomic nuclei, enabling chemistry. Yet in that first picosecond, they were fundamentally different. They all shared a crucial property: they were massless. The consequences of being massless are absolute. In physics, a massless particle must travel at the cosmic speed limit, the speed of light, approximately 299,792 kilometers per second. It cannot slow down or rest. This primordial state was therefore a chaotic storm of particles, each one moving at the speed of light. They were functionally similar to photons, the particles of light. It is impossible to construct stable objects from components that can only move at the speed of light. They cannot be contained or bound together into complex structures. An electron moving at light speed could never be captured by a proton to form a hydrogen atom. Its energy would be too great. Quarks, which in our universe are bound within protons and neutrons by the strong nuclear force, would have been unable to form these stable configurations. The strong force would have had no opportunity to bind them. Without atoms, chemistry is impossible. Without chemistry, stars cannot forge heavier elements. Without heavier elements, rocky planets cannot form. And without planets, biology as we know it cannot exist. A universe of exclusively massless particles is a universe of unstructured energy. It would expand and cool, but it would remain a thin, featureless fog of radiation. It contains the ingredients for reality, but lacks the instructions for assembly. In the language of physics, this chaotic, unstructured state is one of profound symmetry. In this early inferno, the fundamental forces of nature also behaved differently. Today, we observe four distinct forces: gravity, the strong nuclear force, the weak nuclear force, and electromagnetism. But in that hyper-energetic state, electromagnetism and the weak force were unified into a single entity, the electroweak force. This unification, a perfect symmetry where massless particles and unified forces were dominant, is mathematically elegant. For a universe to create structure, however, this symmetry had to be broken. The universe needed to transition into a more complex, less uniform state. The glitch in the perfect machine. For decades, this presented a fundamental problem in physics. Scientists observed a world of massive, slow-moving objects, yet their most successful theory of reality, the Standard Model, predicted in its most elegant form that all fundamental particles should be massless. The theory described the primordial state perfectly, but it failed to explain the universe we inhabit. This was a significant discrepancy. The mathematical framework of the Standard Model insisted on a massless reality. To manually add mass terms into the equations would violate the underlying principles of the theory, leading to mathematical inconsistencies, such as probabilities exceeding 100%. In the early 1960s, a number of physicists, including François Englert, Robert Brout, and Peter Higgs, began to address this problem. They investigated how particles could acquire mass without breaking the foundational symmetries of the governing equations. Their research led them to a revolutionary concept, drawing on ideas from other areas of physics like superconductivity. They proposed that the solution lay not with the particles themselves, but with the vacuum of space. They theorized that the vacuum was not empty, but was instead filled with an invisible, omnipresent field. This was the genesis of the Higgs field. The proposal was that all of space is permeated by this field. In the extremely high-energy environment of the early universe, the field was inactive, having a value of 0. Particles moved through it without interaction. This was the era of perfect electroweak symmetry and massless particles. According to the theory, however, this zero state was unstable, analogous to a pencil balanced on its point. As the universe expanded and cooled to a critical temperature of roughly 10 to the power of 15 Kelvin, the Higgs field underwent a phase transition. This is similar to how liquid water, when cooled below 0 degrees Celsius, transitions into a structured ice crystal. The random, symmetric arrangement of water molecules is broken as they lock into an ordered lattice. In the same way, as the universe cooled, the Higgs field spontaneously settled into a new, non-zero value that permeated all of space. This event is known as electroweak symmetry breaking. At this moment, the vacuum of space acquired a new property, allowing it to interact with particles passing through it. The idea was that particles acquire mass by interacting with this newly activated field. The strength of this interaction would determine a particle's mass. This mechanism, proposed in 1964, solved the problem of mass while preserving the mathematical consistency of the Standard Model. It introduced mass not as an arbitrary addition, but as the natural outcome of a spontaneous process. For nearly 50 years, however, it remained a theory. Proof required the discovery of its associated particle, an excitation of the field itself. The search for this particle, the Higgs boson, became a primary objective of modern physics. The ultimate switch and the cosmic molasses. The moment of electroweak symmetry breaking, occurring 10 squared seconds after the Big Bang, fundamentally transformed the universe. The Higgs field acquired a non-zero value everywhere in space. The vacuum was no longer a neutral backdrop. To visualize this, one can use the analogy of a crowded room representing the universe, with the people representing a passive Higgs field. A person who is not well known, representing a massless particle, can move through the room unimpeded. Now, imagine a famous individual enters. She is immediately surrounded by a cluster of admirers, impeding her movement. Her interaction with the crowd gives her a form of inertia. From an outside perspective, she appears to have gained mass. She is harder to move and harder to stop. This is analogous to the Higgs mechanism. Before the transition, all particles moved unimpeded at the speed of light. After the transition, the Higgs field was activated. Certain particles, like quarks and electrons, interact with the field, attracting a conceptual cluster of virtual Higgs bosons. This interaction, this resistance to motion, is what we measure as mass. Different particles interact with different strengths. A top quark interacts very strongly with the Higgs field, which is why it is the most massive fundamental particle known. An electron interacts more weakly, resulting in its much smaller mass. Neutrinos interact very weakly, which is why their mass is so small as to be nearly zero. The particles of light, photons, do not interact with the Higgs field at all. In the party analogy, the crowd parts to let them through. As a result, photons experience no resistance and continue to travel at the speed of light, remaining massless. This mechanism explains why different particles have such varied masses, and why some have no mass at all. It is all a function of their coupling strength to the omnipresent Higgs field. Another visualization is to think of the Higgs field as an invisible, viscous fluid, a cosmic molasses, that filled space after the transition. Some particles, like photons, are unaffected and pass through without resistance. Other particles are sticky and experience a drag from the molasses as they move. This resistance to motion is their mass. The stickier the particle, the more massive it is. The consequences were immediate. As the universe cooled further, newly massive particles could slow down to speeds less than that of light. This was the critical turning point. Quarks, no longer moving at light speed, could now be bound together by the strong nuclear force into stable groups of three, forming the first protons and neutrons. The first components of matter had been created. The symmetry was broken, and the universe had developed substance and complexity. The stage was set for the formation of atoms, stars, and galaxies. A universe of substance. The emergence of mass via the Higgs mechanism was the architectural event that structured the cosmos. With quarks bound into stable protons and neutrons, the universe now contained the nuclei of future atoms. The next step required electrons. Having acquired mass, electrons were now slow enough to be captured. Approximately 380,000 years after the Big Bang, the universe had cooled sufficiently for massive protons to capture massive electrons, forming the first stable atoms of hydrogen and helium through the electromagnetic force. This event, known as recombination, rendered the universe transparent. Light that had been continuously scattering off free electrons could now travel freely. This ancient light is what we observe today as the cosmic microwave background radiation. The most significant consequence of mass was that it gave gravity a force to act upon. Gravity is exceedingly weak compared to the other forces, but it has an infinite range and is always attractive. In a massless universe, gravity would be ineffective against particles moving at the speed of light. But in a universe filled with massive, slow-moving atoms, gravity could begin its work. Over millions of years, gravity began to pull these atoms together. While the primordial clouds of hydrogen gas were almost perfectly uniform, minuscule quantum fluctuations from the Big Bang had created regions of infinitesimally higher density. Gravity acted on these regions, pulling in more gas, which increased their density and gravitational pull in a feedback loop. Over hundreds of millions of years, these gas clouds collapsed under their own gravity. The pressure and temperature in their cores increased until nuclear fusion ignited. The immense pressure fused hydrogen atoms into helium, releasing vast amounts of energy. The first stars lit up the universe. These first-generation stars were massive and short-lived, ending in supernova explosions. These explosions forged heavier elements, carbon, oxygen, iron, and dispersed them into space. This enriched material mixed with the remaining hydrogen to form new clouds, which then collapsed to form a second generation of stars and, this time, planets. The heavier elements, possessing mass, clumped together into dust, then rocks, and eventually, through countless collisions, formed the planets of solar systems. On at least one such planet, the elements forged in an ancient star assembled into complex molecules. Those molecules eventually gave rise to life, and that life, over billions of years, evolved into a species capable of investigating its own origins. Every step in this cosmic history, from the first atom to the first star, from the first planet to the first thought, was contingent on that event in the first picosecond. Without the Higgs mechanism granting mass, there is no gravity to form stars. Without stars, there are no heavy elements. Without heavy elements and planets, there is no us. Our existence is a direct consequence of a broken symmetry. Every atom in our bodies owes its substance to this invisible field that permeates all of reality. The fragile reality. Our existence appears to be contingent on a phase transition in the first picosecond of time. This raises a further question, which is an active area of research in theoretical physics. Is the current state of the Higgs field stable? This concept is known as vacuum stability. The question is whether the energy state of our vacuum is the true, lowest possible energy state, or merely a false vacuum. Returning to the analogy of the pencil, the state before the switch was unstable. It fell over into our current state, which can be pictured as a shallow valley on the side of a large hill. Within this valley, our universe is stable. However, if a much deeper valley, a true vacuum, of lower energy, exists, quantum mechanics suggests it's possible for the field to tunnel through the energy barrier separating the two states. If this were to happen at any point in the universe, a bubble of the new, true vacuum would form. Inside this bubble, the Higgs field would have a different value, and the laws of physics would be fundamentally altered. The masses of all particles would change or vanish. Chemical and atomic structures would disintegrate. This bubble would expand outward at nearly the speed of light, replacing our vacuum with the new state. The probability of this event depends on the precise masses of the Higgs boson and the top quark. Decades of measurements at particle accelerators like the Large Hadron Collider, LHC, provide the data for these calculations. The current data suggests that our universe is likely metastable. This means we are in a false vacuum, but it is an extraordinarily long-lived one. The energy barrier separating us from the true vacuum appears to be so large that the calculated lifetime of our vacuum is trillions of times longer than the current age of the universe, on the order of 10 to the power of 100 years, a timescale that is functionally equivalent to forever. While our reality may be theoretically fragile, it is practically stable. The fact that the parameters of the universe place it so close to this line between stability and metastability is itself a profound clue that may point toward deeper physical principles not yet understood. Researchers continue to measure the properties of the Higgs boson with increasing precision, searching for any deviations from the standard model that might hint at new physics responsible for our vacuum-specific state. The discovery of the Higgs field confirmed that the properties of our reality are the result of a specific cosmic history. It has also opened up deeper questions. Why does the Higgs field have the specific properties that lead to symmetry breaking? And why are the fundamental constants of nature tuned to values that permit a complex, structured, and long-lived universe? The study of the Higgs boson is the study of our own cosmic contingency. It reminds us that our existence is predicated on a set of physical conditions that are both intricate and, from a certain perspective, remarkably fragile. Why anything exists at all? There is a question that sits quietly behind all others. It is not about how the world works, but why there is a world at all, why there is something, rather than nothing. It's a question that has drifted through philosophy for thousands of years, but it's also a question that modern physics is beginning to touch. Our story of the cosmos suggests it began with an event we call the Big Bang, a moment of pure energy nearly 13.8 billion years ago. From that first state, everything we are, and everything we see, came to be. But there is a quiet, profound problem written into this story. A dark secret in the laws of physics themselves. The Big Bang should have created nothing. It should have been a perfect, balanced explosion of matter and its opposite, antimatter, each destined to cancel the other out, leaving behind only a vast, empty universe of light. And yet, here we are. You, me, the stars, we are the survivors of a conflict that should have had no winners. This is the story of a slight imperfection, a tiny crack in the rules of reality that allowed everything you have ever known to exist. It is the story of how, against all odds, something stable emerged from chaos, and a cosmos filled with quiet structure was born from the ashes of annihilation. To understand our improbable existence, we had to go back to the very first moment. In the instant after the Big Bang, the universe was a cauldron of unimaginable energy. And from this energy, particles and their opposites, their mirror images, burst into existence. We call them matter and antimatter. For every electron with its negative charge, an anti-electron, or positron, with a positive charge was born. For every quark, a fundamental piece of a proton, an anti-quark was made. Our best understanding of physics suggests this should have been a perfectly symmetrical process. Matter and antimatter should have been produced in precisely equal amounts. This is where the paradox begins. Matter and antimatter are mortal enemies. Whenever a particle meets its antiparticle, they annihilate each other in a flash of pure energy. A perfect cancellation. If the early universe had truly held a perfect balance of the two, the story of the cosmos would have been brutally short. Imagine a space filled with countless pairs of dancers, each with a designated partner. The moment the music starts, every dancer finds their partner, and in a flash, they vanish. After a fleeting, brilliant moment, the dance floor is empty. This is what should have happened to our universe. A furious, instantaneous storm of creation and destruction, followed by an eternity of emptiness. The cosmos should have become nothing more than a thin, silent sea of photons, particles of light, expanding endlessly into the void. There would be no galaxies, no stars, no planets, and certainly no one to ask why. The universe, according to the very laws that seemed to govern it, was destined for nothingness. The existence of you, the planet you're on, the star it orbits, is a quiet contradiction. We are the living evidence that the universe had a flaw in its design, a glitch in the perfect symmetry of creation. Our existence is the primary clue that something, somewhere, went wonderfully wrong. The solution to this existential puzzle seems to lie in a tiny, almost insignificant imbalance. The perfect symmetry between matter and antimatter wasn't so perfect after all. Sometime in those first fiery moments, the rules were subtly broken. For every 1 billion antimatter particles, the universe appears to have created 1,000,000,001 matter particles. When the Great Annihilation began, when the cosmic dance of destruction started, almost everything was wiped out. A billion particles of matter met a billion particles of antimatter, and a storm of pure energy was unleashed. But after the dust settled, after the last pairs had vanished, a tiny remnant was left behind. That 1 in a billion survivor, that infinitesimal leftover, became the foundation for everything. You are made of these leftovers. Every atom in your body, every star in the sky, every galaxy in the cosmos, is constructed from the matter that survived this primordial war. We live in a universe built from the scraps of a near-total annihilation. But why did this imbalance happen? This is one of the greatest unsolved mysteries in all of physics. Scientists call it baryon asymmetry. One of the leading ideas revolves around a phenomenon known as CP violation. In essence, it means that some particles and their antimatter counterparts do not always behave as perfect mirror images of each other. This subtle difference was first observed in the 1960s in the decay of certain particles. More recent experiments have confirmed this asymmetry elsewhere, showing that some matter particles and their antimatter counterparts do not decay at exactly the same rate. This provides concrete evidence that the symmetry is not perfect. However, the amount of this asymmetry we've been able to measure so far is not nearly enough to explain the massive imbalance we see in the cosmos. The standard model of particle physics, our current rulebook for the universe, doesn't seem to have the answer. It suggests there must be some new physics, some unknown particles or forces at play in the extreme conditions of the early universe, that tilted the scales in favor of matter. The Russian physicist Andrei Sakharov proposed a set of 3 conditions necessary for this to happen. First, there must be a process that can change the net amount of matter. Second, the symmetries between matter and antimatter must be violated, as we've discussed. And third, these things must have happened out of thermal equilibrium. In the chaotic, rapidly cooling environment of the very early universe, there simply wasn't time for things to balance back out. While the exact mechanism remains elusive, the consequence is clear. The universe is not the product of perfect balance, but of a fundamental flaw. We are the result of a sleight of hand in the laws of nature, a cosmic preference, however small, for substance over nothingness. The Great Annihilation was not a complete success, and in its failure, the possibility of a material universe was born. The war between matter and antimatter was over in less than a second. But the universe that remained was far from the one we know today. It was a place of unimaginable chaos, a state of matter so extreme it pushes the boundaries of our understanding. This was the era of the quark-gluon plasma. For the first few microseconds, the universe was a searingly hot, dense soup of fundamental particles. The temperature was in the trillions of degrees, so high that even the building blocks of atoms, protons and neutrons, could not hold together. Instead, their constituent parts, the quarks, roamed freely in a sea of gluons, the particles that carry the strong nuclear force. Imagine water heated so intensely that not only does it boil into steam, but the very atoms of hydrogen and oxygen are torn apart into a plasma. The quark-gluon plasma was an even more extreme version of this. It was a state where the fundamental bonds of matter itself had melted. Protons and neutrons would form for an instant, only to be immediately ripped apart by the sheer energy of their surroundings. In this quark soup, the rules of reality were still fluid. The universe was a chaotic, indifferentiated plasma, without any of the stable, composite structures that define matter today. This presents us with a second moment where existence itself hung in the balance. If the universe had remained in this state, if it had failed to cool below a certain critical threshold, the quarks would have never been able to bind together permanently. Without stable protons and neutrons, there could be no atomic nuclei. Without nuclei, there could be no atoms. And without atoms, there could be no chemistry, no stars, no planets, and no life. The universe would have remained an eternal, formless fog of free-roaming particles, a cosmos devoid of structure and complexity. This period was a crucial crucible. The universe was filled with the raw ingredients of matter, the survivors of the Great Annihilation, but they were in a state of pure chaos. For anything more complex to emerge, for the journey towards stars and galaxies to even begin, the universe had to pass through another critical transition. The fire and fury of the quark-gluon plasma had to subside, allowing the first stable, enduring structures to freeze out of the chaos. Reality needed to harden. The universe continued its relentless expansion, and as it expanded, it cooled. This cooling was the key to everything that would come next. As the temperature dropped, the frantic energy that had kept the quark-gluon plasma in its chaotic state began to dissipate. Around 10 microseconds after the Big Bang, the cosmos reached a critical tipping point. The temperature fell to about 2 trillion degrees. This was the moment of a great phase transition. Suddenly, the conditions were right for the strong nuclear force to take hold. It was as if a switch had been flipped. The free-roaming quarks and gluons were seized by the strong force and confined into the composite particles we call hadrons, including protons and neutrons. This transition was much like water freezing into ice. Above the critical temperature, you have a disordered liquid. Below it, you have a rigid, ordered crystal. In the early universe, the chaotic, liquid-like quark-gluon plasma froze into the first stable, structured particles. For the first time, the universe contained the enduring building blocks of atomic nuclei. The rules of reality were beginning to lock into place. This concept, where new levels of order appear as conditions change, is known as emergence. Stability wasn't a pre-existing feature of the universe, it emerged from the cooling chaos. The very laws that govern the structure of matter only came into full effect when the universe was cool enough to permit them. Particle accelerators like the Large Hadron Collider have been able to recreate these conditions for fleeting moments, smashing heavy ions together at nearly the speed of light. These experiments confirm that this state of matter behaves like an almost perfect liquid, and that as it cools, it does indeed undergo a phase transition where structured particles are formed. We are, in a very real sense, recreating the moment the universe's first stable matter was born. This great freezing was a pivotal turning point. The survivors of the matter-antimatter war were no longer just a chaotic swarm. They had been organized, packaged into the protons and neutrons that would form the nucleus of every atom in existence. The universe had taken its first, crucial step from a homogeneous soup to a cosmos of distinct, stable objects. But the story of matter's stability was not yet secure. Even with protons and neutrons, the existence of a stable atom was far from guaranteed. Another, more insidious threat, rooted in the classical laws of physics, had to be overcome. With a universe now populated by stable protons, neutrons, and electrons, the stage was set for the formation of the first atoms. An atom, in its simplest form, consists of a positively charged nucleus with negatively charged electrons orbiting it. This arrangement, however, presents a profound and seemingly fatal problem when viewed through the lens of 19th-century physics. According to those laws, any accelerating charged particle should radiate energy. An electron orbiting a nucleus is constantly changing direction, which means it is constantly accelerating. Therefore, a classical electron should be continuously losing energy as light, causing it to spiral inward and crash into the nucleus in a mere fraction of a second. If classical physics were the whole story, atoms as we know them could not exist. Matter would be unstable. The universe would have its building blocks, but they would be incapable of forming the stable structures needed for chemistry and life. The savior of the atom, and of our existence, is quantum mechanics. It rewrote the rules of the very small. It revealed that particles like electrons are not just tiny billiard balls, they also have wave-like properties. An electron in an atom is not a point particle orbiting a nucleus, but exists as a probability cloud, a standing wave. This wave-like nature is the first key to its stability. An electron can only exist in specific, quantized energy levels. It cannot spiral continuously inward because there are no in-between energy states for it to occupy. It cannot fall below its lowest possible energy state, the ground state. But what prevents it from simply being found at the nucleus? This is where the Heisenberg uncertainty principle comes in. This principle states that you cannot know both a particle's position and its momentum with perfect accuracy. If an electron were to fall into the nucleus, its position would become very precisely known. This would mean its momentum would become incredibly uncertain, and therefore, on average, very large. This high momentum gives the electron the energy it needs to escape that tiny space. Quantum uncertainty literally props the atom up, preventing its collapse. Without these quantum rules, matter would be a fleeting, self-destructing phenomenon. The stability we take for granted, the solidity of the ground beneath our feet, the integrity of the molecules in our cells, is an illusion from a classical perspective. It is only because of the strange, probabilistic nature of reality at the smallest scales that atoms are stable, and that a complex universe was able to emerge. The story of our existence is a journey through these incredible concepts. From the cosmic imbalance that allowed matter to survive, to the quantum rules that hold our atoms together, the universe is far stranger and more wonderful than it appears. If this kind of calm exploration into the fundamental nature of reality helps you unwind, consider subscribing to the channel. We explore these profound questions, and your support helps us continue that journey. Now, let's get back to the timeline of the cosmos, as it finally prepares to light up for the first time. For the first 380,000 years after the Big Bang, the universe had all the ingredients for a cosmos, but it was a place of darkness. It was filled with a hot, dense, and opaque fog of charged particles, mostly hydrogen and helium nuclei, and a vast number of free electrons. Any photons, the particles of light, that existed at this time couldn't travel very far. They were constantly scattering off the free-roaming electrons, like headlights in a thick fog. The universe was hot and glowing, but this light was trapped. The cosmos was opaque, but, as always, the universe continued to expand and cool. Eventually, it reached another critical temperature, about 3000 degrees Kelvin. At this point, the universe was no longer hot enough to keep the electrons and atomic nuclei separate. The positively charged nuclei were finally able to capture the negatively charged electrons, binding them into the first stable, electrically neutral atoms. This event is known as recombination. As the free electrons were locked away into atoms, the fog that had filled the universe suddenly lifted. With the electrons now bound to nuclei, the photons were free to travel unimpeded through space for the very first time. The universe became transparent. The light that was released at this moment has been traveling across the cosmos ever since. As the universe has expanded, this primordial light has been stretched to longer wavelengths, shifting it into the microwave part of the spectrum. Today, we observe this ancient light as the cosmic microwave background, CMB. First predicted in the 1940s and discovered by accident in 1964. The CMB is the oldest light in the universe. A faint, uniform glow that comes from every direction in the sky. It is the afterglow of the Big Bang itself, an echo of the moment the universe first became transparent. Satellites have mapped this light in exquisite detail, revealing tiny temperature fluctuations, variations of just 1 part in 100,000. These minuscule variations are incredibly important. They represent the seeds of all future structure. They were the slightly denser regions in the primordial soup that would, over vast stretches of time, grow into the galaxies, stars, and planets we see today. The moment of recombination not only released the first light but also gave us a snapshot of the blueprint for the entire future of the cosmos. But it was still a dark place. The first light had been released, but the first stars were yet to be born. With the universe now transparent, a new era began, the cosmic dark ages. This period lasted for hundreds of millions of years. During this time, the universe was filled with vast, silent clouds of hydrogen and helium gas. The primordial light had faded and redshifted, leaving the cosmos devoid of any new sources of visible light. It was a universe of darkness, but it was not static. An invisible force was patiently at work, sculpting the future. That force was gravity. The tiny density fluctuations imprinted on the cosmic microwave background were the key. These were the regions where, by pure chance, there was slightly more matter packed together. While the differences were minuscule at first, gravity is a patient and relentless architect. A region that was slightly denser had slightly more gravitational pull, and it began to slowly draw in more gas from its surroundings. Over millions of years, this process began to snowball. The slightly denser regions became significantly denser, forming vast, filamentary structures of gas. This emerging network is what astronomers now call the cosmic web. The less dense regions, in turn, became emptier, forming the great cosmic voids. This was the slow, methodical birth of the large-scale structure of the universe, guided by the unyielding hand of gravity. A crucial and still mysterious player in this process was dark matter. We know from our observations that about 85% of the matter in the universe is not the ordinary matter of atoms. It is an invisible substance that does not interact with light. This dark matter began to clump together under gravity even before recombination, creating gravitational wells, or halos. When normal matter became neutral, it was free to fall into these pre-existing dark matter halos. The dark matter provided the gravitational scaffolding upon which the first galaxies would be built. The cosmic dark ages were not an empty period, but a time of quiet, monumental construction. Inside the densest knots of the cosmic web, the stage was being set for the next great transformation. The silent darkness was about to be broken by the light of the very first stars. For several 100 million years, gravity had been patiently gathering primordial hydrogen and helium into ever denser clouds. Inside the hearts of these collapsing clouds, something incredible was about to happen. As the gas became more compressed, the pressure and temperature at the core began to skyrocket. Eventually, starting around 200 million years after the Big Bang, the core of the densest clouds reached a critical threshold of about 10 million degrees. At this temperature, hydrogen nuclei began to fuse together to form helium. This process, nuclear fusion, unleashed a tremendous amount of energy. The first stars ignited, and the cosmic dark ages came to a fiery end. These first-generation stars were unlike any that exist today. They were forged from the pure, pristine gas created in the Big Bang. They were titans, hundreds of times more massive than our Sun. And because of their immense mass, they burned incredibly hot and bright, shining with a fierce, blue-white light millions of times more luminous than the Sun. They lived for only a few million years before their fuel was exhausted. Their deaths were as spectacular as their lives. When these massive stars ran out of fuel, they collapsed and exploded as the most powerful supernovae the universe has ever known. These explosions were the universe's first great chemical factories. Inside the fiery cores of these stars, and in the crucible of their deaths, new elements were forged for the very first time. Helium fused into carbon. Further reactions created oxygen, nitrogen, and all the way up to iron. The supernova explosions blasted these new elements out into space, seeding the surrounding gas clouds with this new chemical inheritance. This was a fundamentally transformative moment. The universe was no longer just hydrogen and helium. It now contained the raw materials necessary for rocky planets and, eventually, for life. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, and the iron in your blood were all forged in the hearts of stars that lived and died long before our sun was ever born. The intense light from these giant stars also ripped the electrons off the neutral atoms that filled space, reionizing the universe and burning away the last vestiges of the Dark Ages. The cosmos began to look like the universe we know today, a vast, transparent space, punctuated by brilliant galaxies. The journey from the Big Bang to the first stars is a story of survival against impossible odds. Our existence is not a given. It is the result of a series of fortunate events, a sequence of cosmic near misses where reality as we know it almost failed to be. It began with a universe that should have immediately annihilated itself into a sea of light. Yet, a tiny, unexplained flaw in the symmetry between matter and antimatter left behind a 1 in a billion remnant. We are the descendants of that rounding error. Then, in the searing heat of the quark-gluon plasma, the universe existed as a chaotic soup where no structure could survive. It averted this fate in a great freezing, a phase transition where the first stable particles emerged from the chaos. Even then, the atom itself was an impossibility by the old rules of physics, saved only by the strange and wonderful rules of quantum mechanics. From there, gravity patiently wove the cosmic web in the darkness, gathering gas into the nurseries of the first stars. And in the hearts of those stellar giants, the elements of life were forged and scattered across the cosmos. The question, why is there something rather than nothing, may not have a single answer. But what the story of cosmology shows us is how something persists. It shows that stability wasn't inevitable. It was an emergent property, a feature that appeared in stages as the universe cooled. Order emerged from chaos. Structure precipitated from uniformity. You are not just an observer of this universe. You are a consequence of its improbable history. Every atom in your being is a relic of that first broken symmetry, a survivor of the great annihilation. You are a piece of the cosmos that, against all odds, managed to exist. And the fact that you can ponder this question at all is perhaps the most wondrous part of the story. We finally found the universe's missing half. For more than 20 years, cosmology was presented with a fundamental problem. A careful accounting of the universe, rooted in the physics of its very first moments, did not match what we could see today. It wasn't the mystery of dark matter, nor the enigma of dark energy. This was a shortfall of ordinary, baryonic matter, the protons, neutrons, and electrons that form stars, planets, and us. Our understanding of the cosmos, from the Big Bang to the present, seemed to have a piece missing. Imagine our most precise models of the early universe giving us a clear, unambiguous budget for how much normal matter should exist. Then, imagine a careful census of the modern cosmos, tallying up all the stars, gas, and dust in countless galaxies, and discovering that half of that matter was simply not there. This wasn't a small error. It was a profound discrepancy known as the missing baryon problem, and it represented a deep question about our model of existence. This is an exploration of that scientific search. It is a story of how a persistent puzzle in cosmology was ultimately solved, not by looking harder at the things we could see, but by using a new tool to perceive the invisible. And that tool would come from a series of fleeting, powerful radio signals, an entirely separate cosmic mystery that, by chance, held the key to balancing the universe's books. The cosmic census, taking stock of the universe. To understand how half the universe could be unaccounted for, we first need to understand how we take its inventory. This process is a kind of cosmic census, relying on two distinct methods: observing the universe in its infancy and cataloging the universe as it is today. First, it's important to define what we are looking for. This story is not about dark matter, which constitutes about 27% of the universe, or dark energy, which makes up another 68%. Our focus is on the familiar 5% of the cosmos composed of what scientists call baryonic matter. This is a technical term for everything made of protons and neutrons, the normal matter of the periodic table, the hydrogen and helium forged in the Big Bang, the carbon in our cells, the oxygen we breathe. Our first method for counting this material looks back to the universe's baby picture. The cosmic microwave background or CMB. This is the faint afterglow of the Big Bang, a sea of microwave radiation that fills all of space. At about 380,000 years after the Big Bang, the universe cooled enough for stable atoms to form, allowing light to travel freely for the first time. That ancient light is what we now observe as the CMB. This light is not perfectly uniform. It contains tiny fluctuations in temperature, which are the seeds from which all galaxies and large-scale structures would later grow. By analyzing the patterns in these fluctuations, missions like the WMAP and Planck satellites could determine the precise composition of the early universe. Their data was unambiguous. Baryonic matter should make up about 5% of the total mass and energy of the cosmos. This figure, confirmed by a separate method called Big Bang nucleosynthesis, became our gold standard. The budget was set. The second part of the census was to count the baryonic matter in the local, present-day universe to see if it matched. This was a more direct accounting. Astronomers painstakingly tallied the mass of stars in hundreds of billions of galaxies. They measured the vast clouds of gas and dust within them. They accounted for the hot gas in massive galaxy clusters. They added up everything they could directly observe. When they finished, the totals did not align. The sum of all observed baryonic matter in the modern universe was only about 2.5%. Half of what the cosmic microwave background predicted was simply gone. This wasn't a minor accounting error, it was a fundamental contradiction. The cosmic census was short by 50%. And in the late 1990s, this missing baryon problem became a central question in cosmology. The two-decade search, a process of elimination, with a significant portion of the universe's normal matter unaccounted for, the scientific community began a systematic search. The first and most obvious question was whether the initial calculation from the cosmic microwave background could be flawed. This was a serious consideration, as the physics of the CMB is a cornerstone of our cosmological model. However, as new instruments like the Planck satellite provided even more precise measurements, they confirmed the original findings with greater confidence. The evidence became stronger. The budget from the early universe was correct, meaning the matter was truly missing in the present day. The search, therefore, focused on where this matter could be hiding. One early idea was that we had simply miscounted the mass of known objects, like galaxies. This was tested using gravitational lensing, where a galaxy's true mass can be calculated by how much it bends the light of objects behind it. These measurements confirmed our existing estimates and did not reveal any hidden reservoirs of baryonic matter. The next hypothesis was that the matter was locked up in dim, hard-to-detect objects, sometimes called MACHOs, massive astrophysical compact halo objects. Perhaps the universe was filled with rogue planets or failed stars known as brown dwarfs. Surveys were launched to look for these objects by watching for the temporary brightening of a star as a dark object passed in front of it. While these surveys did find some such objects, they concluded there were nowhere near enough to account for the missing mass. Attention then turned to diffuse gas. Astronomers used bright, distant quasars as backlights to search for gas clouds that might absorb some of the light. They found some gas this way, particularly in the halos surrounding galaxies, but again, it was only a small fraction of the missing total. With each possibility that was ruled out, a theory first proposed in 1998 by astrophysicists like Jeremiah Ostriker and Renue Sen, gained traction. Their cosmological simulations, which modeled the evolution of cosmic structures, all pointed to the same conclusion: the missing matter wasn't hiding inside galaxies at all. It was in the vast spaces between them. These models predicted that gravity would organize matter into a vast, filamentary structure known as the asterisk cosmic web. In this structure, galaxies are like bright nodes connected by immense, sprawling filaments of matter stretching across the voids of space. The theory was that the missing baryons were located in these filaments, in a state known as the asterisk warm-hot intergalactic medium asterisk, or WIM. This medium was predicted to be incredibly difficult to detect. At temperatures between 100,000 and 10 million Kelvin, the gas was too hot and diffuse for its atoms to be neutral and absorb light in easily detectable ways. Yet it wasn't hot enough to emit its own light in high-energy X-rays, like the gas found in galaxy clusters. Its predicted density was astonishingly low, perhaps just a few atoms per cubic meter. This medium would be almost perfectly transparent, a ghost spread across the largest and darkest parts of the universe. For years, this remained a compelling but unproven theory. Astronomers found tantalizing hints of it, but the signals were too weak and sparse to confirm that this accounted for the full 50%. They had a likely location for the missing matter, but no tool with which to prove it was there. The solution would have to come from an unexpected direction, born from an entirely different astronomical puzzle. An unrelated mystery provides a tool. While cosmologists worked on the missing baryon problem, a different field of astronomy encountered its own enigma. In 2007, while reviewing archival data from 2001, Duncan Lorimer and David Narkevicius discovered a single, powerful burst of radio waves that lasted for just a few milliseconds. It appeared to come from a distant galaxy, and it was gone as quickly as it appeared. They called it a fast radio burst, or FRB. The nature of FRBs remains an active area of research, with leading theories pointing to highly magnetized neutron stars called magnetars. But for the story of the missing baryons, the source of the burst was less important than a subtle change that happened to its signal as it crossed the universe. This property is known as asterisk dispersion measure. An FRB is a pulse composed of many different radio frequencies. As these radio waves travel through space, they pass through the thin, ionized gas, a plasma of free electrons, that was thought to fill the space between galaxies. When the radio waves encounter these electrons, they are slowed down slightly. Lower frequency waves are slowed more than higher frequency waves. Over a journey of billions of light years, this small effect becomes measurable. The high-frequency waves arrive at our telescopes first, followed milliseconds later by the low-frequency waves. The signal is effectively smeared out or dispersed. The amount of this delay, the dispersion measure, is directly proportional to the total number of free electrons the signal has passed through on its way to Earth. Each electron adds a tiny, measurable delay. Here, two separate scientific mysteries converged. Cosmologists were looking for a vast, invisible medium of ionized gas. Radio astronomers had found a phenomenon whose signal was directly affected by that very same medium. The FRB could act as a cosmic probe, allowing a direct count of all the baryonic matter its light had traveled through. The challenge, however, was that the dispersion measure accounts for all electrons along the line of sight, those in the FRB's host galaxy, those in our own Milky Way, and those in the intergalactic space in between. To isolate the contribution from the space between galaxies, astronomers needed one more piece of information for every FRB: its precise distance. If you know how far a signal has traveled and how much it has been dispersed, you can calculate the average density of the material it passed through. For a long time, this was not possible. Pinpointing the exact origin of a fleeting FRB was beyond our technical capabilities. To finally solve the mystery, astronomers needed a new generation of telescopes capable of both catching these random flashes and tracing them back to their home galaxies. If you find this kind of calm exploration into the mysteries of the cosmos interesting, consider liking the video and subscribing to the channel. And wherever you are right now, feel free to share where you're watching from in the comments below. The final confirmation, connecting the dots. The final phase of this search required a new instrument, which came in the form of the Australian Square Kilometre Array Pathfinder, or ASKAP. This radio telescope array has a wide field of view, making it ideal for detecting random FRBs, and the ability to combine signals from its many dishes to achieve the high resolution needed to pinpoint their origin. For the first time, astronomers could confidently identify the specific galaxy an FRB came from. A team led by the late Australian astronomer Jean-Pierre Macquart used ASKAP to detect a sample of FRBs and, crucially, determine their host galaxies. With the host galaxy identified, they could use optical telescopes to measure its redshift. Redshift provides a reliable measurement of a galaxy's distance from us. Now, for each FRB, they had two critical pieces of data: its dispersion measure, telling them the total matter the signal passed through, and its distance. After carefully subtracting the estimated dispersion from our own galaxy and the host galaxy, what remained was the dispersion caused purely by the intergalactic medium. As they plotted the distance of each FRB against its intergalactic dispersion measure, a clear pattern emerged. The data points formed a nearly perfect linear relationship. The farther away an FRB was, the greater its dispersion. This is exactly what one would expect if the space between galaxies is filled with a tenuous, uniform medium. This relationship, published in a landmark 2020 Nature paper, became known as the Macquart relation. The slope of the line in their plot was a direct measurement of the average density of baryonic matter in the intergalactic medium. The final calculation was straightforward. The team used the slope of this line to determine the density of this cosmic medium. Then, they multiplied that density by the known volume of the universe. The result was remarkable. The amount of matter they calculated, existing as a nearly invisible plasma in the filaments of the cosmic web, perfectly accounted for the amount that had been missing for over 2 decades. The missing baryon problem was solved. The baryons had been there all along, just spread incredibly thin throughout the cosmic web, confirming the predictions of cosmological simulations. Since that 2020 paper, the evidence has only grown stronger. Further studies have added many more localized FRBs to the plot, and each new data point has fallen along the Macquart relation, solidifying the conclusion. More recent work has refined this census, suggesting that about 76% of all normal matter is in this intergalactic medium, with another 15% in the diffuse halos around galaxies. Only the remaining 9% is locked up in the stars and gas inside the galaxies we can easily see. The case was closed. Conclusion: the invisible universe and the persistence of matter. The resolution of the missing baryon problem is more than just an answer to an old puzzle. It is a profound affirmation of our cosmological model. The fact that measurements of the universe in its infancy could so precisely predict the total amount of matter that must exist today is a testament to the power of our understanding of the cosmos. The books balance, and in doing so, they reinforce the story of our universe, from its first moments to its present-day structure. This journey has reshaped our view of what the universe is. We tend to focus on the bright points of light, the stars and galaxies. But this discovery shows us that most of the ordinary matter, the substance we are made of, exists in a state of near invisibility. It resides not in the bright hubs of the cosmic web, but in the dark, sprawling filaments that connect them. The discovery serves as a lesson in cosmic humility. It is a reminder that what we see is only a fraction of what is actually there. Even setting aside dark matter and dark energy, most of our own kind of matter is hidden from direct view. It shows that reality is often found not in the luminous and the obvious, but in the subtle and the diffuse. The solution itself represents a convergence of scientific fields, where a tool developed to study one mystery became the key to unlocking another. In solving this problem, however, we are faced with the scale of the mysteries that remain. We have now completed the census of the familiar 5% of the universe. But the other 95%, the dark matter that sculpts galaxies and the dark energy that drives cosmic expansion, remains almost entirely unknown. Finding the missing baryons was not the end of the journey. It was securing our foundation. With the map of the normal world now more complete, the exploration into the vast, unknown universe can continue. The cosmic glitch that made everything exist. Everything you see, everything you are, it shouldn't exist. The stars in the sky, the ground beneath your feet, the very atoms in your body, all of it is a ghost. A leftover from a cosmic war that should have ended in total, mutual annihilation. In the first moments after the Big Bang, a perfect balance of matter and its twin, antimatter, should have wiped each other out, leaving nothing but a featureless void of light. But it didn't. Somehow, when the universe was forged, the scales were tipped. For roughly every billion particles of antimatter, the universe mysteriously created 1,000,000,001 particles of matter. This is the story of that cosmic glitch, a tiny imbalance, a 1 in a billion rounding error that prevented oblivion and left behind the raw material for every star, every planet, and every person who has ever looked up and wondered, why are we here? This is the story of how the universe cheated its own death. We're going to journey back to the very first picosecond of time, to a moment of unimaginable heat and density, to find the origin of this life-giving mistake. We'll explore the cosmic rulebook that demanded our annihilation, and then we'll hunt for the clues that tell us how that rulebook was broken. This isn't just a question of physics, it's the ultimate question of existence. Why is there something, instead of nothing? The perfect beginning. To understand the glitch, you first have to understand the perfection that came before it. Let's rewind the clock, all the way back. Past the Earth, past the first stars, past the first atoms. We're going to a time before time as we know it had any real meaning. The first trillionth of a second after the Big Bang. Here, in this primordial inferno, the universe was a place of terrifying, beautiful simplicity. The four forces of nature we know today, gravity, electromagnetism, and the strong and weak forces, were likely a single, unified superforce. The entire observable universe was squeezed into a space smaller than a single atom. The temperature was an almost unimaginable quadrillion degrees. At that heat, nothing we recognize could exist. No atoms, no protons, not even the quarks that build them. The universe was a seething, incandescent soup of pure energy. A perfect, uniform sea of light. This is a state of maximum symmetry. In physics, symmetry is a profound concept. It means if you do something to an object, like flip it in a mirror, it stays the same. The early universe had this in spades. It was almost perfectly smooth and its laws were perfectly balanced. And from this perfect balance, particles would be born. Through Einstein's famous E=mc², this pure energy could spontaneously crystallize into pairs of particles. A high-energy photon could vanish, and in its place, a particle and its corresponding antiparticle would pop into existence. An electron and a positron. A quark and an antiquark. And here's the crucial point. For every particle of matter created, the laws of physics demanded the creation of a perfectly equal and opposite particle of antimatter. It was a strict, one-for-one cosmic accounting policy. Nature, it seemed, was perfectly fair. This was the battlefield where the fate of the universe would be decided, a realm where matter and antimatter were being forged in perfectly equal measure. And in that perfection lay the seed of absolute oblivion, the rules of annihilation. So, what exactly is this nemesis we call antimatter? It's not science fiction, it's very real. An antiparticle is an almost perfect mirror image of its matter counterpart. A positron has the same mass as an electron, but a positive charge instead of a negative one. An antiproton has the same mass as a proton, but a negative charge. For a brief moment, that early universe was a frantic, chaotic dance of creation and destruction. Pairs of quarks and antiquarks would flash into existence, exist for a fraction of a second, and then almost immediately find each other again. And when matter and antimatter meet, they don't just collide. They annihilate. It's the most complete destruction known to physics. When a particle touches its antiparticle, they both vanish. Their entire mass is converted back into a flash of pure energy, gamma-ray photons, just as E equals mc squared predicts. They cancel each other out, leaving nothing but the light they came from. So, picture the scene. The universe is a boiling cauldron of energy. A photon becomes an electron and a positron. They find each other, poof, they annihilate back into a photon. Another photon becomes a quark and an antiquark. Poof, back to light. It was a furious, perfectly balanced cycle. If the rules were followed perfectly, the destiny of our universe was sealed. As the cosmos expanded and cooled, the energy would eventually drop below the point needed to create new pairs. The creation phase would end. What happens next is inevitable. With no new particles being born, the existing matter and antimatter would continue finding each other. Every last electron would find a positron. Every last quark would find an antiquark. Annihilation would continue until one side was gone. But since they were created in perfect balance, there would be no winner. It would be a total wipeout. The result? A universe with no matter at all. No protons, no neutrons, no electrons. No atoms to build stars, no elements to form planets, no chemistry to give rise to life. The cosmos would have become a vast, dilute, and ever-cooling soup of photons. A cold, dark, empty graveyard of light. This is the paradox. The physics we see in our labs predicts an empty universe. But you are here, reading this on a planet made of matter, in a galaxy made of matter. When we look out, all we see is matter. We don't see the telltale gamma-ray flashes from the borders of matter and antimatter galaxies annihilating each other. Our universe is overwhelmingly made of matter. So, something must have gone wrong. Or rather, something must have gone profoundly, beautifully, and existentially right. The perfect symmetry had to be broken. A cheat code had to be entered into the system. The 1 in a billion glitch. In that first crucial moment, the perfect balance was betrayed. The one-for-one accounting policy had a loophole. Our best measurements today suggest that for every 1.6 billion photons left over from the annihilation, there is a single baryon, a single particle of matter like a proton or neutron, that survived. To put it simply, think of it like this. For every billion antimatter particles, the universe cooked up just enough extra matter to leave one survivor. Let that sink in. It wasn't a 50-50 split. It was a tiny, almost imperceptible flaw. At first, this surplus would have been completely swamped by the relentless cycle of annihilation. A billion particles of matter were instantly destroyed by their billion antimatter counterparts. It was a particle apocalypse. The vast majority of everything ever created vanished in a blaze of glory. But when the smoke cleared and the last of the antimatter was annihilated, something was left over. That tiny surplus of matter, roughly one particle for every billion that were destroyed, survived. That's us. That's everything. Every star, galaxy, planet, and living organism is the leftover scrap from the Great Annihilation. We are built from the rounding error. The universe as we know it is made entirely from the 1 in a billion particles of matter that had no antimatter partner to dance with into oblivion. This imbalance is what physicists call the baryon asymmetry of the universe. The fact that we have a universe of baryons, protons and neutrons, without the corresponding anti-baryons is the single greatest clue we have that the laws of physics are not as perfectly symmetrical as we once thought. Imagine a coin-flipping machine that's supposed to be fair. You run it 1,000,000,000 times. You expect about 500 million heads and 500 million tails. Instead, you get 500 million tails and 500 million and 1 asterisk heads. That one extra head is our universe. An outcome so unlikely it screams that the coin itself is biased. The game was rigged from the start. This tiny bias is one of the most important numbers in cosmology. If it had been 0, we'd have an empty universe. If it had been much larger, the universe might have been so dense with matter that it collapsed back in on itself long ago. The value seems precariously tuned for a universe like ours to exist. So the question is no longer, why is there something instead of nothing? It's now, what mechanism, what subtle imperfection, biased the cosmos in favor of matter? This is one of the deepest mysteries in science, and physicists are in a race to find the source of this life-giving glitch. The cosmic investigation. In 1967, the brilliant Soviet physicist Andrei Sakharov outlined the precise, testable conditions a universe would need to meet to end up with a surplus of matter. These are now known as the Sakharov conditions, and they're the holy trinity for any theory of baryogenesis, the birth of baryons. Sakharov condition 1. Baryon number violation. The first condition is the most radical. A law had to be broken. In all the physics we see every day, baryon number is a conserved quantity. Protons and neutrons have a baryon number of +1. In any reaction, the total number before and after is the same. You can't just create a baryon out of thin air. But Sakharov argued that for matter to win, this law had to be violated in the early universe. There had to be some exotic process that could change the total baryon number. A loophole in the accounting had to exist. Theories that try to unify the fundamental forces predict exactly this, and they also predict that protons themselves should eventually decay. Huge underground experiments like Super Kamiokande in Japan are searching for this decay. So far, they've seen nothing, but the hunt continues. Sakharov condition 2. C and CP violation. The second condition is more subtle. It demands the violation of two fundamental symmetries: charge conjugation, C, and the combination of charge and parity, CP. C symmetry says that if you swap every particle with its antiparticle, the process should behave identically. If this were perfectly true, any reaction that created baryons would be mirrored by another reaction creating antibaryons, for a net result of 0. So, nature must have a slight preference for matter. Physicists learned in the 1950s that the weak nuclear force violates C symmetry and also parity, P, which is like mirror symmetry. For a while, they thought the combined carbon monophosphide symmetry was perfect. But in 1964, an experiment showed that this too was a lie. Nature, at a very subtle level, violates carbon monophosphide symmetry. This proved that the laws of physics are not exactly the same for matter and antimatter. There is a real, measurable difference in their behavior. This is the linchpin. Recent groundbreaking results from the LHCb experiment at CERN have provided our clearest look yet at CP violation in the decay of baryons, the very particles that make up our world, confirming this isn't just theory but a real feature of our universe. Sakharov condition 3. Departure from thermal equilibrium. The final condition is that the universe must have been out of thermal equilibrium. Thermal equilibrium is a state of perfect balance, where any reaction is happening at the same rate as its reverse reaction. If you were creating an excess of matter, the reverse process would be erasing it just as fast. You'd be running on a treadmill, going nowhere. To lock in the surplus, you need to throw the system off balance. The rapid expansion of the early universe did just that. Space was stretching faster than particles could interact. This rapid cooling meant that as heavy, unstable particles decayed in a carbon monophosphide violating way to create the matter surplus, the universe cooled so quickly that the reverse reactions, which would have erased the surplus, could no longer happen. The expansion essentially froze in the asymmetry, slamming the door shut on the symmetric past and locking in a universe destined to be made of matter. The frontier of knowledge. The Sakharov conditions give us a recipe for our existence, but we're still missing the specific ingredients. The biggest puzzle is that all the known sources of this symmetry breaking aren't nearly enough to do the job. The standard model of particle physics, our best theory of particles and forces, does contain CP violation. We've measured it, but here's the colossal catch. When you calculate how much matter-antimatter asymmetry this could create, the number is too small. By a factor of billions. It's like finding a leaky faucet in a house that's been completely flooded. It's a leak, for sure, but it can't explain the scale of the disaster. This means there must be new physics out there. New particles, new forces, new sources of symmetry breaking. And that's what makes this so exciting. One of the most promising suspects is the neutrino. These ghostly particles have a tiny amount of mass and can change, or oscillate, between different types. The theory that describes this allows for a new source of CP violation. Experiments like T2K in Japan and NOVA in the US are designed to spot this. They fire a beam of neutrinos hundreds of kilometers through the Earth and count how many change type, then do the same with antineutrinos. Early results are tantalizing. The T2K experiment, in particular, has shown intriguing hints that neutrinos and antineutrinos do not oscillate at the same rate. The data isn't definitive yet, it's not yet at the high significance needed for a discovery, but it leans towards a large amount of CP violation, potentially enough to explain the entire matter-antimatter asymmetry. Future, more powerful experiments like Hypercamioconde, set to begin taking data around 2027, will be crucial in confirming these hints and could finally pinpoint the source of the cosmic glitch. Other theories suggest the asymmetry was generated during the electroweak phase transition, when the electromagnetic and weak forces split. This would likely require new particles just beyond the reach of our current colliders. The search for the origin of matter is a detective story on a cosmic scale, and the clues are everywhere. We've journeyed to the dawn of time and explored the mystery that allows our own existence. But this story is still being written, right now, in labs around the world. The answer is out there, waiting to be found. What do you think is the source of the cosmic glitch? Is it the strange dance of neutrinos, a secret hidden in the Higgs field, or something even more exotic? Let me know your thoughts in the comments. And if you enjoy exploring the biggest questions in the universe, make sure to subscribe. We have so much more of our cosmos to explore together. So we return to where we started, the profound realization that everything we are is a cosmic accident. A glitch, a beautiful, life-giving flaw in a system that was designed for empty perfection. The vast annihilation at the dawn of time wasn't a failure. It was a necessary cleansing that left behind a universe of exquisite rarity. That single surviving matter particle in a billion is the seed of all complexity, all structure, all consciousness. From that one lonely survivor, gravity could begin its patient work. Over millions of years, these leftovers clumped together to form the first stars. Inside those stars, primordial protons and neutrons were forged into the carbon, oxygen, and iron essential for life. When those stars died, they scattered these new elements across the cosmos, seeding the next generation of stars and planets, including our own. Every atom in your body is a direct descendant of that original, 1 in a billion surplus. Your existence is a testament to the fact that the universe is not perfect. It has a subtle, inherent bias, a flaw, and in that flaw, we find the space for everything we know and love. The next time you look up at the night sky, remember what you're truly seeing. Not just distant suns, but the glowing embers of the greatest victory in history. The triumph of something over nothing. The beautiful, improbable, cosmic glitch that made everything exist.